So you want to learn core classification. You go on YouTube, search about it, then somebody on YouTube throws you with logistic regression, and probably they teach you dot fit using sklearn, and then they take some Kaggle data sets, clean that in 2 minutes, and then evaluate it, and then you get 92% in accuracy, and boom, you're done. And pause for a while and think, is this it? Now, what if I tell you that AI can do this, the same thing, but probably 100 times better than you? What you can do, you can give GPT a messy data set, and then once GPT has that messy data set, it can go and clean it and accordingly train a classification model, and not just train, but also interpret it in the way the real data scientists or machine learning engineers would do, and then build a very nice stakeholder report, which would be further helpful for the businesses and the real task for the data scientists. So your competition for getting a data science job is no longer with others. Not that guy or colleague in your college who has a very good projects, or probably the one who has a very nice Kaggle profile. It's not from somebody who's having great college degrees, but instead it's from a machine that is already 100 steps ahead from you, while doing it rightly, doing it perfectly, and probably doing it much faster than what you would do. So the question is, how do you become irreplaceable into this space? So if the current LLM tools can already write the code for you, can actually execute the code for you, then what are you supposed to do? So it's very simple, right? You have to do it better than AI, but you cannot. You can never ever compete with current LLM trends. But what you can do, you can collaborate with it and probably do better project with AI to eventually beat if AI would do it all alone. And that's what is the next big thing into this space and will actually help you to get a job. See, AI is very fast, it's tireless, but you are the one who will be giving the instructions. You decide what to solve. You choose why this method, not that. You tell AI how to prioritize, where to dig deeper, and what questions actually matter. And that's why I exactly built this course. In this course, I will not just tell you how to use sklearn to predict. I will not tell you how to clean the data set using following some messy framework. Instead, I will turn you into someone who sees raw mess and say that there's a classification problem here. And then you'll be building the logic from the ground to up, not following some particular framework which is out there. You will understand where each algorithm comes from, how it thinks, and where it breaks. And not just evaluate on just one metric, but communicates your insights, you test the assumptions, and then you drive the business action. In this course, I'll turn you into a real scientist and a thinker's approach, like a researcher. Not that somebody who is a data label who has some sort of frameworks to go ahead, they follow those frameworks to do something. One of the key things which we'll be working on is doing a dry run at every phase. For example, that you'll be literally running that algorithm on your paper into the worksheet which you'll be following into the course, so that you know what at every step, what stuff is being used. And then I'm not going to go ahead, take a project and then write the code on top of it and then let you follow it and then you look from it. Absolutely not. I'll give you a capstone project where a lot of instructions and whatever taught is given into that worksheet, into that project file. What you have to do, you have to follow those instructions and use AI, use GPT, use several LLMs, use a lot of stuff already available online, and to be able to develop that capstone project. You will be doing it everything by yourself just by following some of the guidance. But we are conducting a webinar, absolutely free webinar. Into the webinar, I'll be showing if I were at your place, how would I develop that capstone project. So as this course goes live, I would suggest you also register for the webinar. Before the webinar, get your capstone project ready. In that capstone project, we will talk about if I were at your place, how would I do it? And before we start off with this course, one more important thing. I'm pre-launching my brand new program, not my previous batches, a brand new program on core machine learning and MLOps with soft skills, a thinker's approach. What we do is learn from first principles. I help you to develop and thinking ability over memorization or learning from frameworks or just learning about algorithm, just like in this course. Solving with research style depth and thinking like a real data scientist, and working with AI to not just automate, but how you can use it better to help you solve and real problems out here. Now, I don't want to promote it a lot. I want you to go and read my letter, which is in the description box below. You can go ahead, read about the principles, what we are offering into this course, which starts from very scratch and brings you to an ability that you can survive into this AI space. So without further delay, let's get straight into the course.
Given that you know a lot of stuff now, I would like you to develop this capstone project. Before going to this capstone project, I would like you to practice a few of this stuff, which is DataWars. So when I say DataWars, you can simply go here. I'll just quickly log in into my account, and then you go to catalog. And once you go to catalog, click on probably machine learning, and in the machine learning you go a little bit down and then click on classification in depth with scikit-learn. So this is what you should do. You should start following all the stuff. So it is all about practicing it in a way that that will make you more powerful in practicing a lot of stuff. I mean, it does not give you straight to the answer, but for example, let's do that we here the princess is a classification problem which we want to solve. So basically what you can do, it has a guided project where you use an algorithm and then do the stuff here. So you can practice your algorithmic skills over here at the same time. For example, let's say that you go to Logistic Regression and then you continue the project. And in this, you have a lot of stuff that, okay, you do this as a first step, then you do that as a second step, then you do that as a third step and all that. So what you'll end up doing, that you'll be working on to the several data sets, several problems on DataWars for absolutely free. Now, once you do all of this, then you can do whatever you want. You can actually complete all the tracks, which is not so big project. It's just 25 stuff out here. You'll be understanding each and everything which you need to know about an algorithm and classification stuff. And then you work on this capstone project. All the details, every integrated details is listed out here. I don't want to repeat this once again, but you look at this MD file, go through it, what you need to do, what the breakdown of the task is, what are the phases of the tasks is, and then you develop an end-to-end classification project and deliver the stakeholder report. Once you do that, what will eventually end up happening is, given you'll be having a webinar, which is the link is in the description box below. You can go there and register for the webinar. In live, I'll be working on this capstone project and making it develop, and then you can see how my thinking process of developing a project works as a data scientist who have over half a decade of experience into this field. So let's get straight into the course right away and then do something with it. So before that, we'll be working through the entire process as discussed, and then you can go get started with working on classification on DataWars for absolutely free, and probably you can go ahead and work on this capstone project after this course. Let's straight get into the course content on what you'll be exactly learning throughout this classification course. So the first step is we will figure out why there was a need of learning at the first place and why the machines was brought to learn something. So we take examples of several research papers which originally leaded to these kind of terms like machine learning and its type, and will not name it. I'll not give you a definition. I will go through the research papers. I will talk about it. I'll talk several examples that will make you feel that, okay, this is what the problem is, and that eventually serves our goal of making you a generalizer. Once we do that, we'll talk about, you'll discover where classification is born without even naming it. So probably you will be looking at the problem and then you will be seeing how you can solve this without even using any framework. It's just purely generalizing based on whatever we know. Then we deep dive into classification thinking, which is we build intuition that this is how it works and all that. We don't learn frameworks at all. We just build an intuition to be able to make you a generalizer and learn new stuff in a matter of no time. Then we understand how machines reasons in probabilities. We don't just learn something, but we also understand the inner workings behind it. And not as a formula, that how machines feel their mistakes. Of course, these might be new to you, but how machines feel their mistake. But feeling of the mistake is not enough. We need to go through, make sure that you understand how it is learning, and then you'll be doing a real dry run step by step using a worksheet given in the description box below. And then you'll be evaluating not but all from the first principles, not just one thing, but why everything matters in a decision stakeholder report, not just learning about some kind of formula, but also applying this into a real world data science project and how you can use these metrics to be able to serve your data science as stakeholders better and give them a better report and tell a story that how this could be better. And at last, the diagnostic toolkit, which will help you to make your algorithm better by not changing algorithm, but by working on the data and tweaking a little bit in the algorithms to make it work. So this is what the whole thing is. This is not just about one algorithm, but it's the basic foundation, not just a basic, but the core foundation for a classification in machine learning. For this, you don't need to know literally anything. Just you need to know a little bit of maths, which is still class 11th, and then everything will be fine. After this, we'll be working on a capstone project. Now, this capstone project is told you that, okay, this is how you should be developed, which is told at the end of this video. So as we start with module number 1, I don't want to get into the details of what is machine learning and then directly getting into the types and then directly getting into the algorithm. I want you to, as I said, I'm building this program for a thinking ability. So we'll start by questioning some of the stuff. So let's try to go back, long back, and see the story of patterns, failures, and probably learning. So before anyone invented a model or an algorithm or even termed machine learning a machine learning, they were just people who were trying to make some better decisions. Now, I'll take one example to help you understand this. But before that, let me start by asking you something. Have you ever made a decision and later thought, why did I do that? And of course, that's true. You might have made some decision to choose a particular stream like PCM or probably commerce or some sort of studies, area of studies. And you might have thought, okay, why did I really choose it? And you have a reasoning behind it. You might have looked at the other people and the past data of what they were doing or your interest, and then that's why you choose it. Right. But now, there are certain possibilities that lots of students also regret choosing something or regret deciding on something and which they regret later on. So what breaks in a human decision making and what can we do about it? That's the question which we'll try to answer through this module. It's all about how, even by years and years of experience and probably a lot of data in front of us, how are we able to still get a bad decision or a wrong decision? How we humans is not capable enough to take decisions when we have a lot of stuff in front of us. So one of the example is of a loan officer in 1950s in America. So now what really ended up happening with this guy is in 1950s, it was post-war economy, there was a lot of financial industry trends, and this guy had a career experience in loan processing, customer relations, and all that. So that is the persona which we are going ahead. So he's a senior officer who is 25 years into this job, and he has reviewed thousands and thousands of loan applications. So how he makes decisions towards whether to approve a loan or reject a loan. So to make a problem statement clear, his task is, given a certain features, given a certain candidate, for example, let's assume it's you, and you went to John and you are asking for a loan. So on what features he's deciding to give you the loan or probably to or not give you the loan, basically is those set of features. One feature is gut feeling. Now, gut feeling, which we say that it's based on his own personal experience. It's based on its own instinctive nature. Okay, that's one. Or probably evaluation based on physical presentation or eye contact. It's his personal stuff. And probably looking at your salary and background to assess your credibility to go ahead. So probably looks at your body language, looks at your income, and probably etc. Now, some months later, everything is smooth, but others because of all these feelings, he makes a decision for you, and then you're able to pay up the loan. So it goes smooth. But there are a lot of other guys also coming to him, and he uses the same decision-making pattern to decide whether to give loan or not. And what eventually happens, that those guys defaults. So it's all about that. Because of his thinking process, he might also made some mistake wrong, despite being 25 years into this job, a senior loan officer. And this is a real example. I have taken this example from a research paper, and even after spending so many years in the experience, he's still doing such mistakes, despite of having so much experience into this field. Now, Sometimes, as I said, sometimes he's right. He's achieving some occasional successes, and sometimes he defaults to the loan. It leads to losses and confusion in there. Now, as I said, he's doing this for about 25 years. And why is he still unsure about his decision? He's still skeptical about his decision out here. Now, there's a question to ask. Is there a possibility that he can find a way to learn from all the applicants he have ever seen? And is there a pattern somewhere which he cannot recognize something? So he questions in the research paper it mentioned that is there a pattern which he's missing? Or can he learn from all the decisions he has made before? And these are the two questions which he asked. So he asks, okay, fair enough. What I want to do, I want to reflect on my past loans, which is analyzing previous financial decisions and identify hidden patterns. So given the past, he wants to identify the hidden patterns. Okay, these are the patterns which might be there. And then he learns from those patterns, and then he applies those patterns on the new candidate which comes into the play in his future decisions. So is this something possible out there where looks at the past data, identifies something, learn from that, and then apply something? Is this something possible? And that's the starting point, and that's where we have to know. So even making decisions under uncertainty where outcomes are inconsistent even with experience. So in human decision-making processes, humans were able to not, even with the right amount of experience, they were not able to do it. And that's what led to the term known as data-driven decision-making. And that's one of the famous quote is humans should build a system to look at the past to be able to identify the right hidden patterns and then learn from it and then apply in the future interactions. So I can look at 5 examples, I can look at 10 examples, I can look at 20 examples, but what if there is 2 lakhs examples, 200,000 examples? We cannot learn from it. It's technically unscalable, not scalable too much to be able to go find out the patterns in each of the thing and then try to go ahead and do it. So even with the right experience, you cannot do it. And that's what led to the birth of data-driven decision making, the first seed, which he called this. So I want you to go through a different example, which is misdiagnosis in a New York-based hospital. And this is again a real case study which was done back then, which originated the term of learning. Now, there's a young doctor who examines patients with chest pain. So that's what he does. He examines patients with chest pain. Now, a patient presents symptoms of some chest pain. It might be that that he's experiencing something, and then this young doctor collects some sort of data. So when I say he collects some sort of data, is he collects what it is possibility of age, what is smoking pattern, what is the blood pressure he's having, and all that. So given a patient with a chest pain, he collects all the data, and then this doctor evaluates the symptoms, weighing some more heavily. So for example, if he has a smoking pattern, he might have got up with, okay, fair enough, this guy is having something. So he, instead of focusing on blood pressure according to his experience, he focuses on smoking more and then neglect other symptoms. So what really ends up happening is this doctor evaluates symptoms, weighing some features more heavily. So what really happening is he misdiagnosed the patient with the mild angina, which is a crazy thing, and later the patient dies due to the misdiagnosed condition, because what it has actually was very different than what doctor actually diagnosed. So what really ends up happening is this system, or this doctor, is weighing more on some symptoms and weighing less on some symptoms, and then producing some diagnosis which is ideally the misdiagnosed stuff, and then that's why the patient died. So hospital tried to conduct some research. So what they did an internal review, and this was shocking. It was in a research paper. It stated that different doctors made different decisions for the same symptoms, and the same doctor gave different decisions to the similar patients. So even the same doctor gave different decisions to on different days, even it was a similar patient out there. The reason why, because in high pressure and in high variable environments, human intuition becomes biased. And experience, they don't always scale. Experience cannot scale, but your intuition, a human intuition, becomes biased in the area of high pressure. What might be the doctor might have faced completely different stuff, and then he might have forgotten some few stuff, and then in high variable environments, he made a different decision to the similar patient. Probably that's why. So I don't want to share a personal story in this, but it happened in my family as well. That a doctor was so confident enough and misdiagnosed a family member of mine, and later he died. And this is the real problem, relying on human intuition. He was super experienced doctor. So human intuition is so biased at certain scale. They cannot scale. And then that's the moment, that's the research paper started concluding. Can we trust ourselves blindly? Can we trust our medical professionals blindly? Or do we need help to learn from the past? So when I say this, that do we need to learn from the past, is what if the system looks back? I'll just go ahead and then try to find it. What if the systems could look back to hundreds of past cases and learn what really mattered? So for example, they did an experiment. The hospital only did an experiment. What they did is they took 100 past trauma example cases, and then they mapped the systems to outcomes and then tried to discover a pattern out of it. Only 200 was there. Result, it were having the better predictions than what have expert made stuff. So when I say that you need to put out, even the I mean the pattern which came out of the system was better than expert made as well. So I'll talk about some of this stuff over here, which is the triage crisis, what I'm mentioning, the triage predictions. What they did is, and it is another paper on it, why experience is not enough. When I say experience does not scale, why experience is not enough. So the first point is that so there was a checklist implementation, a rule-based checklist was implemented for triaging patients which are in high emergency, patients which are in low emergency. So they started doing it. So some critical patients are marked as low priority, which led to death of the patients, and some stable patients are rushed into surgery, which is for not focusing on this. So the rules which were implemented based on which a patient was decided to whether to send in the emergency or whether to send into the stabling condition was you using this checklist. And what really ended up happening, that the critical patients were sent to the probably low priority, and not so priority people were sent to the high priority states because of the checklist which was implemented. So what they did, they took past, and then they what really did, they did an experiment. They really went ahead that they found some sort of rules. So they had a checklist. So they were something off. These rules was not evolving. So they might have looked at some sort of data out there. And then that's why I said, what they did, they took 200 past trauma examples. They mapped the systems to outcome and they tried to discover the pattern out of it. Then they made a rule out of it, which was a checklist. Now what really ended up happening, these rules were not evolving. And every patient, and they don't learn because every patient is unique on their own way. So even the rule-based or expert-based systems break down in complex, high-stake decision. And that was the another point of contact. So we'll go through another example to help you better understand. Now, a group of psychologists, it is another research paper states, a group of psychologists in the 1980s started to conduct an experiment. So what they did, they give 50 trained professionals a data set of 100 loan applicants. Each applicant has certain feature, which was sort of, let's say, age, income, credit history, number of dependents, whether they have defaulted or not. So these were the 100 loan applicants in past. So 50 professionals, 100 fake loan applicants, each applicant has these following details. Now what they tell to the experts, these trained professionals, is create your own rule to either approve or reject the loans. So based on these past data, find out a way to approve or reject loan. So what really ends up happening is what they found: no two professionals created the same rules. None of the rules had any high accuracy, and some decision directly contradicted with the data. So and the research states that even the accuracy which was there, if you have just made some random number, it was really barely better than that, these accuracy of this system. So what they did, they implemented a basic rule generating system, a primitive one. So of course it designed something that applicants under 18, 25 earning 30k with no prior credit card has an 83% of default risk. Now this performed better than what humans. So the psychologist concluded that we as a humans, like if we were given one feature that based on the age decide whether this person will probably default or not, we would be able to do it. But as soon as there are multiple features, probably multiple dimensions like age, credit history, a lot of stuff, we humans are not so great at by looking at all those features and deciding. If we were just given age, we might be able to do something. Condition is not too much, but as soon as it becomes high dimensional, we go blind. And this is the another huge realization. That decision making is not just about experience and looking at the past data, but it's our inability to process complexity. We humans cannot process complexity if the number of features increases. So now let's step back and conclude our guts and connect the dots which we have in. The banker trusted his gut to predict whether this person will get a loan or not. The doctor relied on symptoms. The triad team built rules. The psychologist tested expertise. And everyone failed. Over here, even 25 years. Trusted his gut feeling. Didn't work out. The experts who looked at different stuff concluded that, okay, same doctors were giving different decisions on the similar patients on different days. The triad system built rules which were sending high emergency patients to the probably some low priority. And psychologists tested expertise who were not able to build rules than what a primitive system generated out of it. So what really ended up happening? Not because they were not smart, not because they didn't care, but because there were too many patterns which were involved in each of the steps. There was too much data which could have been there. So, and it has no systems to learn from the past. So I leave you with one question, which is, what if instead of hard-coding rules or trusting only intuition, relying on experience, we build a system that learns from the data, which is like, can we build a system that remembers all past decisions while taking a new decision, and that learns from what worked, and that also learns from what did not, and then adapts and evolves with every decision? And that's what we are going to do next. We'll start with a real-world problem. We'll start with a real-world problem, not theory, no math, just a messy decision, and then we try to learn from it. So, what we are technically doing over here in this module is that we are literally going in past, digging in research papers and figuring out how these models, how these thinking process of learning from past, what sort of research papers concluded to be able to do this. I would suggest you to go with these three to be able to understand it much more. But this is about the first module, which is the first lesson. And then we go to the next one to figure out, can we learn from the past? So, in the last lesson, we really learned about that what if instead of hard-coding rules or relying on human intuition or experience, we could build a system that learns from the past data, remembers it, and then applies it into and learn from the insights and applying the new decisions. And that's what we call it as a machine learning, and that's what given the birth to machine learning. So now, that's what the concept is. Instead of what we did, really, we followed the thinker's approach. We didn't just told you, okay, this is what the definition is, and then what. We went really through the real problems which scientists faced in order to realize a real problem that, okay, machines need to think. We humans cannot. If the more number of features comes through, we cannot make decisions. If this happens, we cannot make decisions. We can only make decisions if we have the past data, and we can build some system that remembers all the past data while making a new decisions, learns from it, and then adapts and evolves. And that led to the term known as machine learning. So before I tell you a very, very important thing, let's play a quick game. Here are six tasks. What I want you to do is group them into two buckets. Just take two categories. And what you should group them in is based on the way we learn to solve them. For example, predicting if a person will default on a loan based on past data. So probably what I can do, I can look at the past data and predict whether the person and find some insight out of it, and then use that insight, some sort of insights. And then given a new person, I can use that insight or learning which I learned from the patterns from them and predict something. Now, grouping customers into segments based on purchase behavior. So there are a lot of people, there are a lot of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and all these interesting people. What I said, okay, fair enough. These people are probably similar because they purchase similar products. I will explore all the data and then I'll group them into some sort of segments. So there are 3 segments. So here I didn't look at the past examples, but instead I looked how similar they were and grouped them in something. Now, third one is diagnosing disease based on medical history, which is similar to a previous problem, which is looking at my medical history, I will diagnose what disease this guy has. And probably another one is grouping songs by mood from audio features. So again, I'll figure out, okay, these are some of the features, and I will just segment, okay, fair enough. These two guys are together, these two guys are together, these two guys are together. So I'll just group them without looking at the past data. Okay, these are similar enough. They are into same segment. We do it. Now we have another one, which is identifying spam emails from examples. So we look at the past one and then another one, which is organizing by topic. So we again segment it out based on what we see. So we can see one key difference, which is one set of examples out here are nothing but on guided path, which is some had past examples, some did not. Some were about learning a rule and others were about finding structure. So whenever we see a problem, identify literally any type of problem, you can classify into 2 types. Probably one where we are guided by looking at the past and making informed decisions in future. And second one is we just wanted to figure out what's really needed. Just cluster them, segment it out. So when you learn from past examples, which has answers, they are known as guided learning. And when you try to discover patterns without knowing answers, they're like you're exploring and figuring out what really needs to be done. And that's what you have just understood, the 2 of the biggest category of modern AI problems, which is supervised learning and unsupervised learning. Now in this course, because we are just teaching about classification, our focus will be just on supervised learning, and that's the most important part of the program, is looking at this particular feature. Of course, we have a course which is Thinker's Approach where we are focusing on unsupervised learning as well. But in supervised learning, we are given with some past examples, and we have to build a system that looks at the past examples, and then we need to learn from it, generalize from it, and then make informed decisions on the new examples. So one of the ways is diagnosing diseases based on past patients, where we know the past outcomes. Clustering song genres from music features, which is like similar songs, which is there are no labels. Identifying fake currency from examples, which is a labeled data. Predicting student dropout risk based on historical dropouts, which is guided. Another one is segmenting users on your app based on your behavior. They are unguided. So wherever we can learn from the history, that is known as supervised learning or guided learning, and whenever we must discover something new, that is known as unsupervised learning. So when you want to mimic your past decisions, you're trying to learn from what has already happened. So from where you want to see the hidden structure when no one told you what's right or wrong, you're just searching in the segment and the clusters of data. So what we will do, we'll try to take one of these real-world systems, decision-based systems from unsupervised learning, and then we'll try to build a system that looks at the past examples and outcomes and teach the systems to make decisions like we would like it to be done. And that's why we have made this course entirely based on classification tasks. Before I proceed further, I want you to be comfortable in few of the terminologies which I'm going to use. So when I say features, input features, now, input features really means that what data we are providing as an input to the model. And then there is one target feature, which is target feature. What does it mean? What are we trying to predict? So let's take an example of we are trying to predict whether the person will get loan, yes or no, right? Given that we have person age, credit history, income, household, and all that. So these are known as input. Given one is the input features, and yes or no, in past examples you'll be having answers as well, which is okay, this given these things they had paid no, yes or no and all that. Yes, they have paid. Yes, so these are known as target feature, and this given is known as the input feature. Sometimes I interchangeably use also, instead of feature, I use the name variable, target variable. Right? So these are a few terminologies. If you're looking out to clear more out of it, you can just go to my regression course and then watch the first segment on machine learning where I cleared it a lot more better. So yeah, I assume you even had the basic knowledge of the types of the different ML systems. So now our real concept starts. Now you have the brushed up topic. Now you know where it came from. Now you know, okay, we can classify this into two types. Not just we went to definition, but we really went to examples to find out the hidden structure and then thought about it, thought about a solution. So now let's go ahead and build a real world decision making system where we are able to classify, okay, this guy has this, will be able to get a loan or not, a system which learns from the examples. Fair enough. So we are now at the thinking model. So the course started by promising you that I'll help you to generalize. I'll help you that you can learn the next algorithm in the next 5 minutes by understanding the core. And I will not want you to go ahead and teach you the same frameworks and all those things. What I want to do is I want to take a problem. I want to solve step by step by figuring out the problem, figuring out the solution, figuring out the problem, figuring out the solution. That's what I was. that's what exactly I want to do. So the point is, what if you have to build a brain that makes yes or no decisions? Now we need to make a brain that makes yes or no decisions. Fair enough. It can be any task. It can be that you have to build a system that takes in age, credit, whatever number of input features, and based on it decide whether to give a loan or don't give a loan. This is the point which I'm trying to make. So what really ends up happening is we need to build something, a brain sort of thing, which takes in the input features, and then predicts what can be possibly done. So let's take an example. You have just joined a startup named CredWise, and there's a startup named CredWise as well. Apologize if I've taken the wrong name. So what your job is to review the loan applicants and decide, should this person get a loan, yes or no? So just like in a research, they have given 100 data sets, previous applicants to the trained professionals, you're given 100 previous applicants with their possibly these input features and this as a target variable to predict. Now, so what you do, you begin analyzing. What do? You look at trends. Most people under 25 with 30K income were rejected. People with high credit score usually got accepted, but then you find exceptions. So when you look at these trends, you find exceptions. For example, okay, so the people, if the income is above 40K and credit score is above 700, approve the loan. Now, you created this system based on some of your understanding of the trends, and then you tested on 20 new applicants, and your logic will break. Because you have tried to fit in all those edge cases and exceptions where your model or system is not generalizing. So for example, I want you to take one example that you literally there's one chapter in your math book, which is, let's take an example of some sort of, so every chapter contains examples, several examples, right? Several examples. Number 2 is example number 3 and all. And based on these examples, every chapter has their own set of problem statements. Now, every problem statements will have its own set of problems, which you need to solve by looking at examples. But these questions are not similar to examples, right? They are specifically our generalized version that they give examples to generalize on new problems, right? And then you have an examination. In that examination, you again generalize from whatever you learned. So you don't try to memorize it, right? You don't try to find exceptions that, okay, that was the example like this, and then this is the example. You don't try to make rigid rules. You don't memorize, right? You try to generalize it to new problem statements or new problem statements and then try to figure out the solution. Sometimes you're right, sometimes you're wrong. Now, if you try to do that rigid sequences, you'll get absolute 0 in your mathematical examination because no questions are similar, no numbers are similar, every problem is unique, but they can be similar, but they cannot be same. They can be same, but they cannot be similar. So whatever can happen. Now, you're trying to do something, but usually, you find exceptions. Now your logic will break. So what do you do? So instead of trying to say, okay, direct yes or direct no, can we be diplomats? So you know about diplomats, right? They don't say yes, they don't say no. They try to be in a neutral position. They try to reason their answers, right? So what can you say? Can you say something like, I should say how likely someone is to default. Probably I will say that that person has an 80% chance to default. That person has 20% chance to default. And now let the business or stakeholders decide what should be the ideal criteria to figure out. Or you can build a system to be able to figure out, okay, everybody is having less than 50% of the chance, then we should not go ahead with that guy. People having more than 50% of the chance of repayment of the loan, we can just go ahead with that. So you try to be a diplomat. What you do, you say, okay, fair enough. I will tell you how likely someone is going to default. I will not tell you exact answer. I'll be a diplomat. So you build a scoring system. So whenever you imagine a scoring system, what can you do? So let's understand. When you see a cat, your brain, how it works. When you see a cat, how it works. You see a beautiful eyes. You see a beautiful and their behavior, they are very different than dogs, right? You directly compare them with dogs, right? So your eyes have some set of formula to be able to decide a cat, that this is a cat. For example, you won't focus more on his stomach, right? You don't focus on his legs. You probably focus on his features of its behavior. You probably focus on how small it is. So those features of a cat is more important to you than its leg, right? The sound of a cat is more important than you than its shadow, right? So there are some features in a particular thing which holds more important than certain features. So that's how your brain operates. Brain can suddenly recognize something. For example, you go ahead and you see some mathematical examples, right? When you see that mathematical example, you figure out, okay, fair enough, I have seen this. Why? Because you know that at that particular example, they have asked this similar question. Now, when you say similar, you have some parameters on how you're making it similar. You might have said, okay, fair enough, this question comes from ratios and proportions, and in the ratios and proportions, this was in this particular feature. So you put emphasized on more on particular feature rather than focusing, okay, this question might be from triangle. Absolutely not, right? So this is what happens, that what you do, based on all these features which you were given, which is age, monthly income, number of existing loans, credit score, your mind, what it does, it assigns weights. It assigns, okay, how important this is. As of now, let's call this W1, W2, W3, W4, right? So probably the person credit score might be more important than person age. The person monthly income might be more important than a person's age. The number of existing loans might be more important than even credit score, right? Or monthly income. So what you do, you multiply each feature, because you need to figure out that how important the feature is by in weights, like, okay, because that's how the brain operates. They multiply with something. Then what you do, you add all of them up. So if the score is high, they're relatively safe, because they're all important, just understand in this way. And if they're not important, then the weight might be 0, 0.1 or something. Then the score is low, then it's risky. Right? So for example, some person has an age of 20, monthly income 20K, number of existing loan 2, credit score 750, whether they have defaulted, probably let's say yes. Now, what do? You multiply with some weights. Weight number 1, weight number 2. We'll figure out what these weights are. As of now, you can take any random numbers out there, which is just like, okay, 5 for age, 10, because of course it will be greater than age. Existing loan, 15 is of course greater than monthly income. So this is how you determine the weights. Weights are a very important part of the learning process. But just for your brain to understand, you assign something, you add them up, and then what you do? If the score is high, it's safe, and the score is low, it's risky. But you just now told, I would like to someone tell is how likely, which is like in probability terms, how likely someone is to default. So probably if age is a negative, minus 0.1, you'll get a negative, or you'll get something extremely large number. You need to find that you can put that particular number between 0 to 1. So if you get 15, you can convert that into 0 to 1 so that you can later convert. For example, 15 is converted to 0.5. You can say there is a 50% probability or chance, or 50% is likely that someone is going to default. Or probably there is 0.1. There's 10% it's likely that somebody is going to default. Probably 90% likely that somebody is going to default. So you need a way to squeeze a negative number to between 0 to 1. You need a way to squeeze the extremely large number between 0 to 1. So in regression, what really ends up happening, what you're trying to do over here, you're trying to make a linear combination, which is nothing but you're multiplying every feature with its weights and then adding them up with some biases if everything remains 0. Of course, I would like you to see some regression lecture that will help, but if that's okay if I'm not read. So basically what you're trying to do, you're trying to multiply each feature because you want to understand what is important, add them up, the score is high, you go ahead. But this will not tell you how likely someone is going to default. We can't just say, I mean, number can be literally 1,000 and another number can be just 1. You cannot say anything above 500 is good, high score, anything above 500 is not good score. You cannot say that. You need to squeeze that in a probability terms to go ahead. And that's what happens. That this thing is a straight line, right? It can take literally any amount of numbers. This is nothing but a straight line in your X and Y paragraph. What if we can make this and this between 0 to 1, which is like squashing these scores between 0 to 1, which now, so when I say 0 to 1, it's like this S-shaped curve. So anything goes beyond 1 does not becomes 1, but really becomes 0.99999, but cannot be 1 because we can be, as we told, we are a diplomat. We'll never agree on something, but we'll try to give our estimation. We will be acting like a diplomat. So over here, it's 0.999. Anything which is above 1, the more 9, the bigger the number is. And then probably anything which is below 0, negative, you go to like, okay, fair enough. I'll go to 0.00001, but not in negative. So that's what it tries to deal with. That we build some S-shaped curve. What it does, it squashes your particular. We'll come to that, what these S-shaped curve, how these are built and everything. Don't worry about it. The point I'm trying to make that is that you need to see that, okay, fair enough. Given the input feature, what importance your brain will focus on some more important feature, then add them up, but the score is high, we need to produce some likely, we need to get some probability. So there's a system that squashes these numbers between 0 to 1. Now when you squash the number, you'll be getting like, let's say there's one score 100, right? It is squashed to 0.92. So you can say, okay, the applicant has a 92% chance of repaying a particular loan. So what do you do in this squash system, you give a weighted score, that is, if the score is high, if the score is low, which is a linear combination of your weighted features and input features. And then it gives an output, which is a probability between 0 to 1, how likely somebody is to pay the loan, or your problem statement can be how likely somebody is not pay the loan. So what we did, we just built a system that starts with features, weighs them with something so that we understand the importance of every feature, and gives a probability of a yes or no outcome. And it does not say yes or no, but it gives a likelihood of how something is going to happen. And this is what the world calls logistic regression. Now you see how you have learned it. Without I ever named logistic regression, you learned how it worked. And this is what the scientists came to. Scientists told, if I focus on these important features, fair enough. What I can do, I can add them up, multiply them basically, add them up if the score is high. But I cannot tell them, I cannot even classify them. How can I classify 1,000 number? I need to get them between a probability area. So there should be some way to think about in terms of, okay, I can put them in an S-shaped curve. So anything goes above 1, I can put them 0.999, but never 1. And anything goes beyond 0, which is negative, which is 0.001, but never in the negative scores. Because probability rule is the axiom is it will always between 0 to 1. So that's what the world calls logistic regression. So what it yields, we give the initial data inputs with importance, which is weighted features, for example, and then it multiplies the weight importance of weights with these features, for example, with age, with credit score and everything, so that we know how important each feature are, then adds them up. Then what it does, it gives some raw z. I'll call that term z, which is a linear combination of x1 multiplied with the weight plus x2 multiplied with another weight and all that. So this is the z. Then what do you do, because it is a linear combination of a number, a very, very large number or negative number, what do? You squash them up into using a S-shaped curve. So anything above it is always, above 1 is always 0.999, anything below is 0.0001. So you output a curve, which helps you to determine, okay, fair enough, this is what is the likelihood. So let's try to build a system. Let's say you're an assistant at a bank and a person walks in to apply for a loan. So what do? You collect some basic information, which is they're 28 years old, they have 45,000 as an income, the credit score is 720, and they already have one existing loan. Your job is to help the bank decide should this person get the loan or not. So as I told you correctly, not all details matter equally. Because human tendency is to, like we told in a research paper suggested that we are very bad, and as soon as the more number of features increased, we can add tens of features and a human will be bad at it. So what do? As you go through more and more, you start noticing credit score usually matters more than age, as I was saying. High income often means they repay, but not always, as I said, because they might have existing loans. People with many existing loans tends to default because they have a lot of liabilities on them. These are the patterns which you notice. So what do? You start weighing every features, which is the person's income is good, the credit score is strong, one existing loan is fine, age is okay too, I can give the loan. So what you're doing, you're not doing any math. You're adding up a feeling. That's why we add it. You understand the inner synergy. You're just adding up a feeling of how safe this person seems by multiplying your thought process, your gut feeling, your brain. This is how the brain is working. You're multiplying the thought process of the brain with some input feature and then adding them up to give some output. And that's the beauty of the brain. Machine learning is all about how your brain works. Nothing here and there. It's all about how a brain works. Now, you have the feeling. You need to convert that feeling into a decision. So instead of saying yes or no outright, you start thinking in percentages. Like this person feels like 90% safe bet. Though that one yesterday felt like a 30% risk. This one, maybe 55% chance that they will pay up. So your brain start creating a scale. Not just like a blunt person like black and white. I'll never say that you'll ever get a job. There's a 90% chance that you can get but there's still 10% chance that you might not. A diplomat, which is a good sign that you're reasoning your output rather than just saying yes or no. So you're not sure about that, but how you feel. The more positive signals, the closer to 100. The more risk factors, the closer to 0%. That's how your brain will think. The more, okay, this person adds this person, the more positive signals, the more negative leads to this. And that's what leads to this curve, which is the more positive signals, you start to think like that. So you're thinking like a fur, one that starts low, rises quickly, then flattens near 1 when it is positive, and flattens when it is negative. And that's how your brain operates. And that feeling, that's what we call as a sigmoid function. What it does, once you have a feeling that, okay, fair enough, it converts that feeling into something, which is it converts your added up feeling into a percentage. That's what the sigmoid is. So without knowing it, you have built a mental decision curve. So small changes in input, small nudges in confidence. Big positives, steep jumps. Beyond a point, you stop being more sure, because you can never be 200% sure, right? So beyond a point, okay, you have had enough positives, like hundreds of positive. Okay, this guy will pay a loan. Instead of just being 100, 200 positive, you can just flatten out, right? And you just flatten out, okay, this guy is too much negative. I don't need to really look at other features to determine. And I just say, okay, I do want to give the loan to this guy. So this is what happens. And that's the beauty. And that's what the sigmoid function is. You have built a mentally decision curve. System has a name. You look at information, you mentally give some importance to each thing, combine those to form a gut feeling score, and then you convert that gut feeling score into a yes or no decision. That gives you a likelihood something using a curve, and that's what we know as logistic regression. So whenever somebody asks you, and you have not just learned logistic regression like, okay, you multiply, you do this, you have literally mimicked and look out every problem to be able to build something out of your brain. Whenever somebody asks, you will remember that this is how your brain operates, and you'll start relating that this is what logistic regression was. So machine learning is never about algorithms. It's always about mimicking your brain, finding problems, finding a different one, and here we go. We have a name towards it, and everyone has a name towards it. So here we go. Now let's try to put the numbers on the gut feeling we just built. So of course we have a feeling, the brain. Now let's try to put in the numbers. How do we do it? It's very simple. Priya is 27 years old. She earns 50,000 rupees a month. Her credit score is 730. She has no previous loans. So your system need to turn her data into a decision which we need to go forward with. So let's call these age, income, credit score, etc. is the features, because of course, which I told you. And this is what the tables are. So do you think, as I told in Nizar, not all features are equally valuable. So do you think credit score should matter the same as age? Absolutely not. Should having 0 or 3 existing loan matter the same as 5K difference in income? Absolutely not. So the systems, of course, uses weights to decide how much importance to give to each feature. So what do? We assign some weights to every feature. For example, this particular thing, age is assigned 0.02, monthly income is assigned 0.1, credit score is assigned 0.004, and existing loan is -2. Of course, this does not make sense, of course, because it randomly put weights, because these of course, existing loan will have a better weights. So what do? Your gut feeling says, okay, I'll combine everything, which is like positives and negatives. So we add up important weight version of the features, which gives us something like this. Now this Z, which we call, is known as system's raw confidence. But there's a problem. What does 8.546 mean? That's what I was exactly saying. What if we got something like -6.2, -9.1, -10.1 and all that, or 29.1? How can we compare these numbers? We cannot put some threshold based on the system. Of course not. We cannot do that, because it violates the mathematical way of linearly understanding something. So we need a way that squashes. That's what your brain was. That creates a curve that anything beyond this point, I'll consider them as gray. 0.9999. Anything below this is 0.0001. But I'll never go above 1 and below 0. And that's what we call as a normalization, that's what the sigmoid function does. And sigmoid function formula looks like this, which is, this is a sigmoid sign. Given your raw confidence, it converts that into a particular probability that squashes them 0 to 1. Now, if you want to know about how this sigmoid comes to, of course, because it is not really needed, but I want you to know, I have attached a resource. You can go ahead, look at it, do a research on how the sigmoid function was derived. It's a pretty interesting feeling. Or we have more materials where we have literally given how these sigmoid functions are made or derived. So our system thinks that this girl has a 99%, so you approve the loan. Now there are some questions to ask. Why do we multiply feature by weight? Why not add or divide? There's age, why you multiply, why not plus, why not divide, why not minus, and all that. Because multiplication as a fundamental rule scales the influence. It says how much does this feature push the decision, which means how much does credit score will push the decision as compared to age. Of course, credit score will push more than age. That's why we multiply. That's why we don't add or divide. So multiplication scales the influence. Because if you see the startups have ever made their influence by multiplying, not by adding up or dividing it. Additioning is not compounding. It's all about compounding. Fair enough. So why some all weighted features before applying the curve? Because we are not blending the influences into a decision score, which can be converted in between 0 to 1. Because we have to blend everything. That's why you mix it up, right? That's why you add it. Addition is about blending. Multiplication is about scaling. And why use this sigmoid curve specifically? There are a lot of others. So of course there are a lot of which squashes, but what it does in this case, it's smooth and continuous. It does not stop at something. It's continuous. So that the more the 99, and at one point it becomes obsolete sort of thing. It maps everything and it is easily differentiable. We'll learn about why the activation functions needs to be differentiable. Of course, you don't need to know right now. You can ignore this point, but it is easily differentiable at this point of time. Now imagine you don't manually decide these weights. What if the system could learn from the past data and then do something? So let's understand a story. Whenever a baby comes up, whenever he tries to recognize something, for example, his dad, my dad has a bigger nose, he has a bigger hair, he has this eyes, and he has this beard. The baby will learn from his feature that this person is mine. So instead of looking at his hands or probably legs, he will notice his voice, hair, and all. So the baby gives importance to the certain features of a particular person in order to recognize that person. Or even Evie as a person. If we see something new, okay, I've seen you somewhere because you look somewhere similar to, one Bollywood actress. Your eyes look similar. So we are looking at the features. We are giving importance to those. We'll be giving weights to those things, right? That's how the brain is operating. So we need to give a way to our machines that how would it know that what weights to pick? Human have a tendency, we'll learn, we'll go ahead because it's all about how humans operate, that's it. And how would it use those weights to make better decisions over time? So what we need is some mechanism to decide weights for us. We cannot give random weights numbers, right? We cannot give, which one you should focus more on. You should make sure that it learns without giving it a rule. So I hope it makes sense. Now let's get to the next part of the program, which is more and more interesting. So hey everyone, welcome back to the next one, which is how the machines feels mistake. So let's do an exercise. Now tell me, if you are learning something, what is the process of learning? Process of learning is probably doing something, making mistake, and then realizing that it was a mistake. Right? If you don't realize it was a mistake, you won't learn anything. So that's why, in the philosophy also we say that you need to really realize something, that you accept that you have done wrong, then only you'll improve. Otherwise, there's no chance that you'll improve. So how can we, because see, model has given some prediction, and how can we make machines feel? That's what we are going to learn. How can we make that human capability, but at scalable point of view? So we built a smart system to predict whether someone will repay the loan or not. And this is our usual example, Priya, which has age this, income this, and credit score this, and existing loan is this. So you feed her your details in your logistic model, which is like everything, which will have the weights and yeah, everything will have its weights, and then you add them up and then pass them through a sigmoid function that will yield between 0 to 1, as we have discussed in the last one. So this states, okay, your prediction 8.82. So what do? You went through all the internal weights, weighs them up, and passed it through a sigmoid, which is your raw score. And then it says, okay, fair enough. When you pass through the sigmoid function, it yields to 0.82, which is your 82% chance that Priya will repay the loan. That's what your prediction of the system was. So she paid some EMIs. Of course, she paid some EMIs, but she defaulted. She didn't pay it, which means that your system was wrong. The actual label, which is your y in this case, y is nothing but your target variable or target feature, is 0, which means that she defaulted. So instead of she defaulted, we write 0 and defaults, which means 1. Only it can be either 0 or 1 as an output variable, not in both of it. So your system predicted 0.82, which is strong confidence in repayment, but actual label was that she defaulted. So it's not just a mistake, but it's a confident mistake. For example, you were confident, so much confident that you know that it's 82% chance that she will not do it. So it's not just a mistake, it's a confidence mistake. So now your system must now feel this confidence mistake and make sure the next time the confidence is low if the actual label is y equals to 0. So now, if you need somebody to feel really the mistake, that's why the system of jail and stuff is there, to make them really feel that they have done something wrong and make sure that other people don't do the same, is how do we punish this mistake properly? Not just a mistake, but a confident mistake. It was not just a mistake. He was confident, and he took all the data in past to be able to make that decision. So he was confident in that, but still he did it. So how do we punish that mistake properly? So one way is, okay, how can I punish? Is say that, okay, actual minus predicted. So actual was 0, prediction was 0.82, which is 82%, which is minus 0.82, which is of course not helpful. It's a direction that it was minus 82% away from the actual value, which was the person defaulted, but actually 0.82. So it was away, which is minus 8.2 away, which is 82% away from the actual value. So it's a direction, not a punishment. So what we do, we square it up. Which means we double that punishment, whatever the minus is. So it yields to 0.67. So what if the system predicted 0.999 for repayment? So bigger punishment, from 0.67 to 0.9, because the difference is huge, than 0.8. He was 82% confidence that person will repay the loan, but she did not. But now he's 99% sure. So it's a bigger mistake, right? Bigger confident mistake. So let's try 0.999. He's more. He's like, okay, it's very similar. So you can see that it is pretty gradual. The more the confident mistake are, the more it should be punished. That's the idea of it. So we square it up. So the punishment should explode as the model gets confident into the wrong direction. So the more, see, for example, the punishment of that's how the IPC and cases are made, right, in India. So if you just, steal something, so you might have to pay some penalty. You cross some red light stuff, you have to pay some penalty, right? If you don't have a driving license, you pay some penalty. So that punishment of that is obviously comparable to when you kill somebody, when you do something with somebody, when you really do a big crime. So you're confident enough, you are in full conscious while doing it. So of course you'll get more punishment than actually somebody who's just crossing the red light. Of course he knew about it, so that's why he got penalty towards it, right? For example, one of the way to understand this is a driver who was unconscious, who got heart attack in the car and then hit somebody. Okay, fair enough. I mean, of course not fair enough, but or a guy who has a full confidence and drunk and then driving. He was full confident enough. So the punishment for the drunk guy who hit the guy should be exploded more than the guy who got heart attack. So we need a better way to punish confident mistakes. So if the confidence is too much in the wrong direction, the punishment should explode, should be more like that. So how likely is that the system would predict 0.82 when the truth is 0? So it gave only 18% chance. Then how likely is that the system would predict that the person has an 82% chance when the truth is actually 0? It's 18% chance that she would default, which means the 100 which is 1 minus 0.82, which is 18 out here, which tells, okay, 18% chance that she would default, but she actually did. So the probability of the correct event happening given the model belief is 1 minus your prediction, which is y hat in this case, 1 minus 0.82, which is 0.18. So there's 18% chance that she would actually default. So this is the likelihood which your system predicted that your Priya will default. But over here, Priya actually defaulted. So the likelihood that the model was correct, we want to minimize this likelihood. We want to minimize the probability of the correct, the wrong event happening, which is we want to minimize this likelihood which we have created right now, or maximize the negative feedback. Of course, that's the end goal, which we'll figure out when we learn about optimization. But to understand how we need a better way to punish it, the way we would work is the probability of the correct event happening is 0.18, which is 18% chance that she would default, given the model belief. So what we do, because we want to give a stronger punishment, just understand we are applying log to give stronger punishment. I'll come back to more detailed approach right now, why we are using log and all. So that is 1.714. Now that's a real penalty, not because it was just off, but because it was confident in the wrong outcome, which is confident mistake. So I'll give you one example, which is a model prediction was 0.82. The true outcome that y equals to 0, which means that she defaulted. Your the probability of correct event happening is 0.18. So your loss is 1.71 by applying the log to it, log to the correct event happening. If the model prediction is 60%, which means that 40% chance that she would default, your loss is little less, because it was less. The more the confidence, the higher the punishment is, less the confidence is, the less the loss should be. If it is 0.1, you can see that the person would likely to be defaulted. So the person defaulted, the model predicted it will default, and 0.0105. So loss is very less as compared to this. So the model starts to give less confidence in the wrong direction, the penalty drops. And that's what I'm trying to make a connection over here. So what if Priya had actually repaid the loan? So let's assume that she had paid, so the model predicted it correctly. So the likelihood is simply y hat equals to 0.198, which means there's low loss, the model was right, and the confident enough. We need a way to combine both of the cases so that it can cover our entire data set. The formula to come to for a loss function is something like this, which is y multiplied by log of your y, which is your, the actual value, plus 1 minus, of course you're adding because you need to combine both of the behavior. So 1 minus your prediction multiplied by log of 1 minus y hat, which is your y hat is your prediction out there for positive, and that for in negative, where you're adding stuff out here. So the closer your prediction is to the truth, the loss approaches 0. The farther and more confident you are in the wrong direction, loss shoots up, as we saw in this particular example, right? So as you can see over here, that's what this diagram states. The closer you are correct. For example, the actual class is 0. So if your predicted probability is somewhere here, right? So sorry, somewhere here, actual class is 0. Your loss is obviously very high, right? But if a probability is somewhere here, where a loss becomes very steep and probably negligible. Same goes with the actual class, which is equals to 1. But our theory remains one of the most important questions which you should ask, which I will certainly add a page on it. Let me just see if I can remove this image. Okay, I cannot really, but let me just tell you why we need a log, why we need to apply log. So let's understand from a story. The story is that you are making a prediction. You are making a prediction that Priya will show up with 80% confidence. So for example, it's like you're building a system which will of course build in a capstone project. That is a candidate Priya, whether she will show up into the interview or not, right? 0 or 1 sort of thing. So your system made a prediction that Priya will show up with 80% confidence, which means 80% is the probability, which is 0.8. So what actually happens? She does not. So the chance of the probability of she not coming up is 20%. So the loss should be high over here. So now the machine asks how bad. Not I know that my guess was bad, but how bad it is. So it needs a way to measure his mistake, but not just like right or wrong, but it needs to punish more. It's overconfidence. In one sense, you can understand. So let's assume that your confidence which your model predicted that she'll show up is 0.99, but she did not. So your log of this 0.99 is minus 0.01, right? Which is the confidence that she will show up. So she will show up, and then she really showed up, which means that she was very sure, and that's the low penalty, negative penalty, that she showed up, and the log that's where the loss is less. But let's assume that, okay, 0.8, 80% chance that she will show up. The log of it is minus 0.22, minus 0.22 if you take the log of it. So over here it's confident but not perfect. Now when you go ahead, you keep on doing it. So let's assume that your model says, okay, the prediction, my confidence that she has a 10% to show up, but she actually showed up, which means that she was absolutely confidently wrong, which means the log of it is minus 2.3, not 0. Minus 2.3, which was, it was confidently wrong. So the loss over here is high. So the log drops sharply as confidence goes down, and that's what we want. Loss is less. Log loss is less if the confidence is good, but if confidence goes down, that's what we see, that okay, it is actually decreasing over the period of a time. Now let's build two possible truths. Let's try to build two possible truths as we were speaking over here, that you want. So if she actually showed up, right? If she actually showed up, which means 1, and your prediction is also 1. So that's one case. That's one case. So if your prediction is 1 and actual value is also 1, then your loss is 0, right? But if your prediction is 0.01, which means so low that she will not show up, but she showed up, so your loss is very high, 4.6, minus 4, something like minus 4.6, right? Now, if the actual label is 0, if the actual label is somewhere 0, so your prediction is 0 and the loss is also fine if the actual label. But if the prediction is 0.99 that she'll show up, but she did not, then your loss is 4.6. Again, so what really ends up happening is the loss is high if you are, it tells you a way, it tells you a measure. If you apply log towards it, it tells you a measure in a certain range of a loss. So what you do, you simply put both of it into the one formula. You simply put it in the one formula, which is nothing but, of course, which we have written over here. This one, right? Now, what it does, this clever formula picks the right log penalty depending on whether y equals to 1 or y equals to 0. So let's assume y is equals to 1, right? So when you calculate it, everything will be fine. So it will figure out, because we have combined it, added it. That's what addition is. It penalizes overconfidence in the wrong answer and rewards certainty in the correct direction. Whether to go in positive or negative side, and help the learn softly rather than just binary right or wrong, 0 or 1. So that's why we add log over there in order to identify the right direction. So for example, in linear regression, if you know about it, we use squared errors, which works well for continuous targets. Over here, we just have probabilities which happens to between 0 to 1. So in square errors make sense when it is about prices or ages, which is a continuous target variable. But for probabilities, it's not sensitive enough to know how confident the model is. So the log loss in a particular is scale sensitive It is specifically designed for probability aware and mathematically grounded in information theory in how much surprise we get when something happens. That's what. So if your model is 90% confident about something and turns out wrong, it should be punished more than if it was 60% wrong. And this is the essence of log-based learning, and that's why we are using logs over here. I hope it makes sense. So this is about how exactly the model should feel mistake. Okay. Now, once the model feels its mistake, feeling a mistake is not enough. Based on the mistake, improving it. So a strategy to improve. And that's what we're going to talk next. So now we come to the another part of learning, which is feeling regret is not enough. So just like when somebody is like, okay, he has done the mistake, he realized his mistake, he got punishment for it, but he does not learn anything. So it's like, usually people say sorry, but it's just like words. If it does not convert to their action, then I mean, their sorry does not mean any value to me, at least. So that's what exactly the question is. That feeling regret is not enough. What does the model do with that regret feeling? How does it improve itself? And that's what we call it as the world of learning. And that's why the learning termed into the play, which is the machines of way of adjusting itself, just like humans to do after they fail something, after they realize that their mistake, after they get some punishment about it. So of course they will realize their mistake if there's something terribly wrong, right? So they learn something and then they improve on top of it. So let's start with an example. So your model gave Priya a repayment probability of 0.82, which is 82% chance that she won't default and 18% chance that she will default. So what it eventually ends up happening, as in the last example, that she defaulted. So your model is now emotionally devastated. So now it wants to correct its thought process. Of course, it has to improve, right? So we need to figure out how it can perform better. When performing better means better weights. So basically, one of the key way to understand, let's say that you need to recognize whether this image is a cat or not. You focus on importance features, right? And now if you start focusing on its fur is similar to dog, right? Or some other characteristic which is similar to dog. So you need to figure out which important features to look out to be able to determine it's a cat. And how and what priority in what priority I should look out for. Just in the case of the loan approval prediction example, we need to look at credit score more than age, probably income more than age, sort of thing. And then we decide how much weight to give even between credit score and income, right? So we need to figure out that, okay, fair enough, I will be able to get to my correct outcome if I'm able to weight something nicely. So if I'm focusing more on important features and giving them the right weights, giving the right weights to the important features and low weights to the low important features, that's what the machines has to do. And that's what it's all about. It's all about finding that right W's, W1, W2, which is the features, which is the weights of those features, that how important my credit score is with respect to my outcome, how important my income is with respect to an outcome, whether the person will default or not, and determining the right weight, not just randomly understanding, but determining the right weights is the key to learning in machines. And that's what it's all about. All deep learning and machine learning is about, and most people don't get it. So your model gave Priya repayment probability. So of course, as I said, so let's try to understand how it works. So let's say a blindfolded archer, the one who is an archer, is trying to hit a target. He's a blindfolded. And every time they shoot an arrow, someone tells them how far they have missed. But basically, how far they have missed. So, but he just don't want to know what they missed. They want to know which direction to turn and by how much, so that they can turn better. So there's a archer and he shoot over here, but sorry. So it's an archer. Let me just take a pen now. Okay. So there's an archer. This is where he has to shoot. Okay. And he shoot over here. So he needs to know, okay, fair enough, which direction to turn and by how much to be able to hit the right spot, so that in the next time he focuses in the direction, but might not be, I mean, too much. So okay, a little bit, 50 meters more, 50 centimeters more, something like that. So this archer needs to know which direction to turn and by how much, so that they can get better. And that's how machines do. So each time they adjust a little. Too much left, turn right. Too little up, tilt more next time. So these ideas it needs to know to be able to perform well. So the archer improves by trial, feedback, and small corrections over the period of a time, which is exactly how a machine learning model improves. So it's like learning from regret, one arrow at a time. So what we do? Just imagine is you take a weight 1 equals to 0.1 and weight 2, which is income and credit. So this is the input feature and this is the weights associated with 0.2, right? You multiply with something and then you get the loss of something minus 2.1, something like that, right? And then you adjust these. So basically when you adjust this to probably 0.001, something like that, 0.001, and then this way to 0.002, and then your loss is better than previous one. Okay, so how do we determine? So the point is, how do we determine that how much to tweak it, in what direction, positive to be going above or below, positive or negative direction, and in what direction and by how much I should go above and down. That's what the point is, and that's what this guy. That's how this blindfolded archer were able to learn to hit the right spot, and that's what exactly machine learning is. So we need to figure out by in what direction and by how much we need to tweak the weights in order to get the loss less, and that's all about. So imagine the mistake number is like your score in a game, which a lower is the better. So the model goal is simple. I want to reduce the loss next time I make a prediction. So the next time I make a prediction with these weights, I should be able to quickly understand, okay, fair enough. Current loss is current loop loss is less than my previous loss. So I'll go ahead with this weights. Now in this weights, I'll figure out, okay, fair enough, how much now my weight is basically 0.001 and my another weight is 0.002. So with this, the loss is less than of course the previous loss, but of course there's some loss. So you determine, okay, in what direction I should go and what by how much to reduce. So your weight becomes 0.002 and weight 0.003, something like that, and your loss is less than the previous. So weights gets updated to this, right? So we need to determine, I want to reduce this number, I want to reduce the loss the next time I make a prediction. So now we are just changing weights, but we cannot really just keep on guessing and determine which weight to change. We need to know which direction should I change the weight in and by how much that will help my loss to reduce. And that's where the concept of slope comes into play. So what is slope? If I change something a little bit, the delta of x, how much my y changes. So if I change something, then how much my y will change. Basically, y is nothing but your loss in this case, and x is nothing but your weight in this case. And the slope tells us, if I change this weight a little bit, the weight of, let's say, probably one feature of income, a little bit, not too much, a little bit, will the loss go down or up? That's the slope it tells. So let's say you're in a curved hill, something like this, you're in a curved hill, and then you don't have a flat map, just the feedback after each step. So you something like, I'll just say this one, curved hill, or probably this one, right? So you take a small step. So over here, can you take out the slope? Slope can be taken out on a straight line by figuring out the change in x with the change with respect to change in y, right? So if you've seen my calculus videos, to determine the slope of a curved lines, because if you plot our log loss, this is how the plotting of the log loss will look like. It's not a straight line, it's instead a very different curve hill. So we need to figure out, okay, you take a small step, because you technically want to reach out to here, right? You want to reach out because the loss over here is absolutely zero, or probably somewhere here, but you're probably you're here because the loss is very high, so your weights are something over here. So you want to ultimately reach out here. So to reach out, you need to figure out in which direction I should go in, or probably you're here, your loss is here, okay, or some, it can be literally anything, something like this, right? So your loss is here. So you need to figure out by in which direction I should go in and by how much I should go in, right? So it says, okay, fair enough. I'm here. I need to come here. I need to come here because my loss is less over here. So if I go in this direction, my loss decreases? It asks the question. Yes, it decreases. So I'll keep going in this way. Now I go again. Okay, fair enough. I go again. I keep on going it. So if I go in this direction and by this pace, my loss is decreasing? Yes or no? If yes, we go. Otherwise, we turn around. That's what's happening. And nothing. It's basically that the trial and error, the slope on a curved line is known as derivatives. So in derivative, what we are trying to really do, if let's assume that we need to reach here and our loss is here. We are sitting currently here. We need to come down here. So to determine which direction to go in by how much, first of all, we need to figure out, okay, if I change this, if I change a weight, my weight is something like, let's say W1 is equal to 0.01. If I change this a little bit, how much my loss changes? So for that, you take a slope, but slope is not possible on a curved line. So what you do, you zoom a lot, and then you find a tiny straight line over there, and then take out the slope of that. Then that's what the derivatives are. Derivatives is nothing but you keep on zooming and zooming and zooming onto this curved line. Keep on zooming and zooming and zooming until you see a straight line. And then you take out the slope of that. And that's what we mean by that derivative. Of course, I don't want to get too much in detail. I have already taught derivative in long back in linear algebra lectures and all. You can go ahead and watch that if you want to know. But derivative is nothing but a slope for the curved lines. And that's what the trial and error direction in mathematically, which is known as the derivatives something. So your weight is how much you trust Priya's credit score. This is basically giving the importance. Your model currently trusted a lot, so that's why she defaulted. So this feature contributed to the wrong decision. So what you do, you try to figure out how much weight of the credit score I can change so that the probability of the wrong decision decreases. So that's how you compute the derivative of the loss with respect to your credit score, which is how much my loss will change if I change the weight of my credit score, right? So it's like if it is positive, increasing that weight increase loss, so reduce it. So if the direction is positive, we said increasing that weight increase loss, so reduce it. If it is negative, increasing that weight decrease loss, so increase it a bit. Right? That's what the derivative tells. Derivative nothing but tells you how, in what direction and by how much you should do. Now keep on naming. So we know the direction. If it is positive, then we reduce it. If it is negative, then we plus it. Now a bit. If you're understanding, what is a bit over here? A bit is nothing but your pace by which you go. So you have to tweak it by your outcome. If you have a big data set, then you might afford to be at a larger set of learning rate. So learning rate, how fast you're going. For example, if it says, okay, fair enough, do one thing, because it is positive, reduce it by probably 10. Your learning rate is 10. So what you'll end up doing, you'll go so much fast that you'll diverge. You don't come here, you go there. So you don't have to also go so much fast and so much slow. Or if you just keep on going slow, you'll never reach to this. So this is known as global minima, which means the loss is absolutely zero. So you keep on going and going and going in that direction by a bit, and the bit which we have to decide, which in the machine learning terms, we call it as a learning rate alpha. So you decide the alpha, and alpha is 0.01, 0.001, 0.0001, depending on your data size, and then you have to also tweak it to be able to understand how well your model is performing, and this is what we call as a hyperparameter. Hyperparameters are nothing but things which you have to decide, model does not learns. So that's what the hyperparameter means, which you have to decide. So how do we update? So let's understand that we now know, okay, we have to increase it, we decrease it. So but how do we update? Because our existing is this, we evaluated the loss, we taken out the derivative, it tells plus it. How do we plus it? How do we update this weight to a feature which we have just concluded? So there we have very simple formula. Your old weight minus your alpha, which is your learning rate, how much you should increase or decrease a bit, multiplied by your derivative, because you are decreasing or multiplying like that, your derivative of loss with respect to that particular feature. And alpha is the learning rate as we decided, and the derivative tells the direction and the strength of that correction. And then when you do it, you'll be getting your new weight for that. And then what you do, you take this new weight, you go ahead and evaluate the loss on it, right? And then you run a loop on it, and then you evaluate the loss with respect to the new weight. And then you'll be saying, okay, fair enough, this loss is obviously lesser than the previous one, but how much to change so that we go a little bit more until and unless we reach at this position where we are okay. So we keep on doing this on every weight and on every data point. So for every weight, because we have a credit score, we have income and all that. So what we need to figure out the ideal weight for everyone and for every data point, right? So that it learns from the data. So every time the model starts hitting the target more often, it yields the right result. So this is how the learning process means. Learning process is nothing but a way to be able to figuring out what is the ideal weight or the importance which we give to a particular feature in order to move ahead. So that's one way to think about it. Now what I want you to do is I want you to do a real dry run. So you'll be having access to a very, very highly specialized data set, which is of 5 data points and with 2 features and then outcome. You have to create a logistic regression model on your paper. So you'll be also getting the guide in your comment description box. Go ahead and see how the learning process happens at each and every step. I have taught you each and everything which you need from starting to end to learning without even going too much into mathematical details, but still you know the mathematical details. You know why we take out the derivative. You know why we do multiply, plus, and all that shit, whatever is there. I want you to do one thing. Because I want you to be a generalizer, I will not spoon feed you. I have given you a very, very comprehensive worksheet. Basically, you have to dry run it. You are given a data set, you have to build a logistic regression model and find the ideal weight and then drop it down and then give it to me in my group. So that's a worksheet which you have to do. Basically, dry run it. Pretty simple. Just follow the worksheet. You'll be at the right path in developing a right set of so basically, you're getting that data set. You have to behave like you're a model, and then you're trying to learn and then try to relate everything which I've stated and then try to mimic it and become a generalizer. And then you'll notice lots and lots of problems in that. And that will make you a generalizer. So the problems which you notice over there leads to the new set of algorithms which is going to come. And that's how you become a generalizer, not just someone else. So yeah, this is it about logistic regression. Now, there's one more important thing. Logistic regression is just one algorithm by figuring out several problems and all. But wait a second. We have a very important logistic regression for it to work. For example, your brain to function properly, it assumes that your hand is fine, your heart is fine, your gut is fine, your legs are fine. You don't have any stress and all. The same way, any algorithm in the world assumes that some things are still fine to be able to, for me to operate properly. So fine, which means in your data, everything is fine. So that's why we look out for assumptions. And let's now go ahead into assumptions. Please, before going to assumptions, please follow the worksheet, which is given in the description box down below. Hey everyone, welcome back to another section, which is classification measures. So this is a new types of notes which we are adopting. So thanks to our team who crafted these notes, researched a lot and created the top-notch notes so that you can review after the lectures. So let's get started actually to talk about classification measures, and it's very, very important topic to understand in terms of interviews perspective as well, or whether in terms of building, machine learning projects, right? So let's get started eventually with it. So the thing which you're seeing in front of me is the classification measures, where what it tells is that, so let's start talking about, here's what my agenda for this whole session would be, to talk about what exactly they are, and then we'll talk about what are the ways we evaluate our model, and then we have several methods, and then we'll talk about elaborate each and every methods in great detail so that it will be easy for you to understand right there. Okay, so we'll be going in depth, having you a better understanding of what exactly we wanted to speak. Cool. So let's get started now. To what exactly classification measures are. Classification measures are the matrix that is used to evaluate the performance of a classification model. It is a way to quantify how well a model is able to accurately classify data into different categories or classes. So basically what it tells is that the matrix which we have, for example, in regression we had some R2 score, right? We have R2 score, we have MSE, mean square error, which was helping us to quantify how well. Quantify means to in the form of numbers. It was telling us how well our regression model is performing, right? So in terms of classification, we had log likelihood as a way to measure the performance of our model. However, we had that was quantifying how well your model is performing. However, the log likelihood has several disadvantages which you will automatically notice in terms of taking out how well your model is performing, how well your model is able to quantify your achievements, how well your model is able to quantify your achievements or performance of your particular model. So basically out here, which you're seeing, the classification measures, they are the matrix which used to evaluate the performance of the model, evaluate how well your classification, which is logistic regression, is performing. And they provide a way to quantify in terms of particular numbers, how well your model is able to accurately classify the data in different categories or classes. For example, if you have the model that classifies into a cancer and non-cancerous categories, then the statement saying how well we have a matrix which quantifies how well this model M is able to accurately classify into cancerous and non-cancerous. Okay, so that's what the classification measures were. So how do we evaluate the model? As we talked about, it's a way to evaluate the performance of a classification model. So exactly how we evaluate our model. We evaluate our models to determine how well they perform on unseen data. So why exactly there's a need to do it? But because why we do it is because that we want to first of all understand how well our model is performing, right? So if you have a student who is learning something in a class, you want to check with them. You just don't want to make them learn. You also want to test them. You also want to understand how well they are performing, right? So that you can further either improve that model or make the student improve by learning more, or even you're good to go to pass to the next class, right? So that's why the same happens over here. We evaluate models to determine how well they perform on unseen data on an examination. You can understand in this way. As I said, evaluation is one of the important steps in the machine learning processes because it helps us to understand the strengths and the weaknesses of our machine learning model and make decisions about which model to use for a given task. Okay. This is like a general discussion on why exactly we use this, but maybe you will worry about what exactly is this. Make decisions about which model to use for a given task. Say for example, you have logistic regression, you have logistic regression, you have logistic regression, and then you have linear regression. You trained, of course, the logistic will win. You trained on classification data. You trained on classification problem. So when you evaluate both of the models, the model for the accuracy for this would be higher as compared to this, right? And that's why you will go with this. Go with that. So let's start talking about each and every cases of. There are several ways that we can evaluate our model. There are several ways we can evaluate our model, or we can say there are several ways which we can use to identify how well our model is performing. So we have accuracy, which is most probably the noobs use, and precision, and then which is a sensitivity, which is a specificity. So basically precision is also called specificity. You will learn about specificity, you listen more of the terms like specificity, sensitivity when you'll work in healthcare domain, However, we'll just go with precision, recall, F1 score, ROC and AUC, log loss, confusion matrix. We have already studied about this log loss, where we had the which you can see in the past lectures, which was our aim was to optimize this negative log loss. So basically we want to minimize the negative log loss in order to maximize our likelihood, right? So that was our log loss, which you've already seen. What I'll do, I'll go through each and every So I'll go through each and every measures, and then I'll ignore this and this as of now, because I want you to prepare a full report on both of this as a part of classification measures, because I don't want to spoon feed you. This is very easy. This is terms of thresholds. So we'll talk about thresholds a bit, so that you can understand what exactly thresholds are. Right, so basically these two are, and this is like a bit challenging as well, so but you'll be getting once you learn about all those things. So let's go to the next lecture, and let's try to understand each and every bit of classification measures. Cool, so let's get started with accuracy, our first classification measure which we want to get started with. Accuracy is a measure of how many predictions made by a model are correct. So basically, you a student sat in an examination, and in that examination you had total of all the way around to 20 questions, and students scored maybe 19 questions or maybe 10 questions well. So accuracy is the percentage or a measure of how many predictions made by a model are correct. For example, if your model made 90 correct predictions. What do you mean by correct predictions? People will have the issue in correct predictions as well. Correct prediction means you know that in test set, when we actually give to a model, when we actually give to when assume with the example of students, assume with the example of a students. So basically assume that a student sat in examination and he has answered some of the questions, right? So now he has answered 20 questions. Now he has answered like MCQs, okay? Then teacher comes and checks it with the real answers, right? With the absolutely correct answers, with the answers which are correct. That's why then they match with the student's answer. So if the correct answer matches with the student, assume that student is a model over here. So if the ground truth matches with the student answer, matches with the when the ground truth matches with the student answer, with the student answer, then we can say that this is a correct prediction. This is a correct prediction, right? And if the student answer does not matches if the real answer does not matches with the student answer, then that's incorrect prediction. So exactly same that works over here as well. If your model answers the answers it correctly, what do you mean correctly? The model prediction is equals to the whatever. For example, model predicted the person has a cancer, but actually the person had a cancer. Then that's a correct prediction, right? But if your model predicted cancer and the person does not have a cancer, then we say that's the incorrect predictions. So accuracy is a measure of how many predictions made by the model are correct. It is often used to evaluate the performance of a classification model, as I said, for noobs. That's why it is often. So imagine you have a test with multiple questions and you have to choose one answer out of 4 options. If you answer all questions correctly, you will have 100% accuracy. So you have several questions, and then you have to, and every question has at least one option out of 4. So if you answer all of them, you will get 100%. However, if you get only one answer wrong, so out of 4 questions, you get 3 questions correct. If you get 3 questions correct and 1 question not correct, then it will be 75% of your answers were correct. 75% were your answers were correct, which means that one question consisted of 25% in your test, right? So basically, that was the very simple example in terms of multiple choice questions. So in a similar way, accuracy in a classification model measures. So basically over here, what you do, we have 75%. What it indicates? It indicates the proportion of your correct answers. So in similar way, classification model measures the proportion of your correct predictions made by the model. For example, if a model correctly classifies 100 out of 120 samples, which means that you had 120, assume that the model has 120 questions to answer. Your model has for example, we have given 120 data points to check whether that person, we have given some information about every individual person, and we want to check whether that person has a cancer or not. And these are 120 examples out there. So now your model says, yes, it indicates y hat 1, y hat 2, y hat 3, all the way around to y hat n. So these are your model predictions. 120 model predictions. Out of these, when we check by our ground truth, it says that only 100 are correct. Only 100 are correct. Then we say the accuracy would be 83, which is the proportion of the correct predictions is 83.33%. 83.33%. So I hope that this makes sense to you. Let's go on the next slide. The next slide says when accuracy fails. So now you know that now you may be thinking, okay, we are getting in terms of accuracies how well a model is performing. So higher the accuracy, if there is 100%, if the higher the accuracy, better your model is, right? So you're wrong, right? First I'll tell you you're wrong. So now let's go to when accuracy fails, when this will never work. So it can be misleading if the class distribution is imbalanced. So let's talk about what do you mean by class distribution. So you might notice that in your class, there might be 90% of boys and 10% of girls, right? So percentage of a split between boys and girls is 90-10, which is an unbalanced split, right? What do you mean by unbalanced split? Unbalanced split means between both categories, boys and girls. 90% of them are boys and only 10% of them are girls. So basically the balance between them is they are not balanced, right? Because 90% are boys and 10%, there is unbalanced split or unevenly split it, right? So it can be misleading in terms. So say for example, you want to classify whether the gender of the person is a boy or a girl, right? So currently this can be accuracy can be misleading. Here, let's understand how with the help of an example. So let us assume if the data set has 90% negative examples, assume that the person has that doesn't have a cancer, and only 10% who has a cancer. Okay, only 10% positive examples. So model will always predict negative. The model always predicts negative. Assume that for every example, model predicts Model for given 120 examples, your model predicts that the particular data point is a negative, like the person does not have a cancer for every particular example. So the accuracy will be 90%. You may ask now how the accuracy will be 90%. Assume that you have 100 samples to classify. Okay, in that 100 samples, in that 100 samples, you have 90% of your examples. 90% of your examples who is non-cancerous. Okay, and only 10% of them is cancerous. Okay, so your model, if your model classifies each and every 100 samples as the person as a negative sample, or that the person does not have a cancer, then it answered 90 samples correctly out of 100. Only 10 got wrong, and that 10, what was that 10? That 10 was the negative positive samples, which he did absolutely wrong over there. 10. So your accuracy is 90%, which says that a model is very good. You might understand it is very good, but you have to notice that it leaded to biased, or maybe you'll say that is very bad. That is very bad, right? 90%. 90% your model says, but the thing is, it correctly classifies all the non-cancer negative examples, but it not even did for even positive examples. That's pretty bad. So you're saying even to the person, so basically we say that is very unfair model, which is saying 90%. How? Because it is very viable. It is saying 90% of your proportion is correct. So you'll understand, acha, 90% is correct, very nice. But the actual truth was that 90 examples were of negative only. So your model correctly classifies these 90. But 10, which is positive, that was not correctly classified. Right? So now assume that your model had 50-50 split. Your model has 50-50 split. What do you mean by 50-50 split? 50 as negative examples, 50 as a positive examples. So if your model has correctly classified 50 but failed to classify another 50, right, then your accuracy would be 0.5, right, 50%. So that's where the model is bad. So you have to understand, it is misleading. It is saying that the model is 90%, the accuracy is 90%, but the thing is that the positive, it is failing. It is not even classifying even one example as a cancerous. So that was the issues in that. So that's what the imbalance problem is. That's where the accuracy fails, where it gives you the misleading results. So you notice over here, balanced and imbalanced data, where you have this is the examples of a balanced data, where your negative samples, negative data points is approximately equals to the positive data points. Okay, 50-50 split, evenly split. But assume that you have you have two categories, which is normal gene and oncogene. Okay, so you have two categories, normal gene and oncogene. So you say normal gene is 90% and oncogene is 10%. So if your model correctly classifies 90 examples, then 90% is the accuracy, right? That is saying 90% of your proportion of your model was correct. So you say that your model is performing well, but the thing is, it is not performing well, because even on the thing, or even on the examples where the model should choose oncogene, it is there, they are not clicking on that. And this is very common, and this is imbalanced dataset problem. Imbalanced dataset problem is very common nowadays. It's pretty much common problem. Let's understand why this is pretty much very common problem as of now, so that it will make sense more to you. So basically why it is common, let's try to figure it out maybe. So here's my point on why it is common. So let us assume that you want to predict whether the person will default on his credit card or not. So you have a data. So you have a data whether the person will default or not, whether the person will so the data which you have, it is mostly viable that most of the person will not default, because you know that can be legal procedure, and it is very rare that someone is doing fraud, right? Not everyone does steal something, right? So it is very obvious not everyone has a cancer, right? So in a company, the fraudulent transactions, or the defaulter would be very less, would be very rare, right? So it may happen that there might be 95% of it, 95% of in your data, the person who never defaults, and there's only 5% which is very rare, because and which who defaulted, which is very rare in that case, right? So you have an imbalance split where your data has a 95% of examples, who have never defaulted, but only 5% as the who have defaulted. So it is very rare. You're not going to default a credit card if you get one, right? Middle class people don't do it. Only high class people do it because they know they can get it out of it. I have never did it, and I think there is mostly 95% even people don't do it. You will see that. Now assume, let's another example. Assume that you have to build a model that identifies whether you have a cancer or not, right? Whether you have a cancer or not, right? Whether you have a cancer or not. That's a very good question. So now out of 10 people, it may be possible not any of them has a cancer, because cancer is also a very rare disease, right? It's not a COVID-19, it's a very rare disease, right? So that's why that also contains a very uneven split. So out of 8 billion population in the world, only millions of were affected. So that's what my point is to say, that it is very rare to get out of 10 people, there might be not even one people who has a cancer. Right, out of 10 fraudulent transactions, there might not be even one transaction so fraudulent. So that leads to that we don't have the data. We don't even have the data, right? So that's an imbalanced data problem. I hope that teaches you something great today, and we'll figure out the solution. And don't worry, we'll figure out a solution of how to fix this imbalanced data problem. I'll tell you some of the ways to tell you how we can fix it. First, we have to collect the data. We can focus on collecting the data which is rare, the data which is rare or which is less in proportion. Okay. In this case, we want to collect the data of oncogene. We have several methods, which is, I think, So we have several other methods for handling balance and imbalance data, which we'll see in our projects, like how do we handle this imbalance and balance data problem. Okay, cool. So I hope that gives you accuracy gives you a very good stance on what exactly accuracy is. Let's go to the next video to talk about something which is super duper amazing, something which is related to accuracy, which you will love to understand. Welcome back. So today what I'm going to do is talk about some of the important terms which you should know, which is very common and very liable to ask in the interviews. So we'll talk about what are true positives, true negatives, and other things which is super duper important for your understanding as well. So let's try to get into it and then try to understand true positives, true negatives, false positive, and false negative, right? So let's get started. So if they assume that you have a classification problem, so let's frame a classification problem. Okay, the person has a cancer, so you have built a model. So you built a model that classifies whether the person has a cancer and non-cancer. The person does not have a cancer. So you built a model that has this characteristics of predicting whether the person will have a cancer and non-cancer, which is a binary classification problem, of course, because we are classifying two of the categories out there, right? So now let's go further and try to think about in terms of several cases. The first one is true positives. So what are true positives? Any instance that is correctly classified as positives. Now let's try to understand. So when your model predicts, so assume that your model predicts the person has a cancer, which means the person, which is true, and if the person does not have a cancer, then that is false, right? If the person has a cancer, that is true and that is false. Okay, so if your model predicts that the person has a cancer, so if the model classifies that the person has a cancer, which is true, and your actual when actually you check it, the person has a cancer. So here's how I'm telling. If your model predicts the person has a cancer, true means the person has a, that's your model prediction. Model predictions, the person has a cancer, and actually when you check it, when that is checked, as you said, when the teacher checks the student paper, so now the doctor checks whether actually the person has a cancer, or you check the ground truth, which is your correct, which is the absolutely correct. So that also says the person has a cancer. If that also says the person has a cancer, then we say that instance is correctly classified as a positive. Any instance that is correctly classified, please note, correctly classified as a cancer. Okay, correctly classified as a cancer. So any instance that is correctly classified as a cancer, correctly classified as a cancer as positive. The person has a cancer as a positive, right? So cancer which is positive, right? And if the person has a cancer, which means the person is positive to cancer, and if the person is negative to cancer, which means the person does not have a cancer, right? So over here what I'm trying to tell that if your model predicts the positive, if your model predicts positive, which means the person has a cancer, and actually the ground truth, the absolute answer, the correct answer was also positive, then we say that's true positive. That particular sample is a true positive. And if your model classifies the person does not have a cancer, which is negative, and your actually the answer is also the correct output is also negative, which means that is true negative. We are saying an instance that is correctly classified, your model has correctly predicted as a negative, as a negative sample, but over here as a positive sample. Fair enough. Go to the next. Assume that your now in these two cases your model has correctly classified as a positive and as a negative. Now let's go further and talk about when your model has incorrectly classified. So what does that mean? So any instance that is incorrectly classified as a negative. I think that's something. Yeah, okay. So any instance that is incorrectly classified as a negative, So your model says that the person doesn't have a cancer as a negative, which means the person does not have a cancer. But that is incorrectly, whatever the model says does not matches with the correct answer. This means that model predicted that the instance belongs to the positive class, but okay, so I think that's a bit of in writing mistakes which people did. So let me just go through and let me just confirm, let me just go and see that what exactly the missplit which they have did. The predict value is positive, but it is false. Okay, so basically I think that is bit of what things has done over here. False positive in this you had over here, which is positive, right? Your model belongs to what is actually the negative class, and false negative where you can incorrectly classified as the negative. Okay, so now apologize for the inconvenience. Let's try to understand these two again. So false negative are those you say for example your model says that the person has a cancer. But predicted that the model has a cancer, but in actually when actually look in a ground truth, it is the person does not have a cancer. So basically that is the incorrect predictions. Your model says that the person is a positive to cancer, but your ground truth says that the person got negative to cancers, got opposite. So basically it is incorrect, where your model says that the person is positive to cancer, but actually it was negative. So that is called the false positive. That is called the false positive. And then we have false negative, where your model says the person does not have a cancer. The person does not have a cancer. And negative means the person does not have a cancer, but actually they had the cancer. My God, if you rely on a machine learning model, and if false negative happens, that is a disastrous thing which can happen, which can even take up your life. So your model says the person does not have a cancer, but actually they got a cancer. So over here, that is called false negative. So let's try to understand with the help of an example. Of another example, let us assume of another example. But before that, let's go to this one. Is, let's say a model is trying to predict whether a person has a certain disease or not. Now we are talking about a certain disease. We are talking about the certain disease. Now we say that a true positive would be correctly identifying a patient with the disease. So what is the true positive? True positives are the one where your model predicted positive, and actually your actual value was also positive, which means they have correctly classified the positive class. The positive class. Okay. In this case, having a certain disease is a positive class, and negative class is not having that certain disease. A true negative would be correctly identifying a patient without the disease. So we say that true negative is also where a model says the person does not have that certain cancer, and your actual was that the person does not have that certain cancer. This is also correct, but that in terms of negatives. That's called true negative. True negative. And then we have another one, which is a false positive, in which case your model says that the person has that certain disease, but actually they didn't had the, which is negative. The person didn't had that certain disease. So that's nothing but a false positive. And then we have false negative, which says that model says the person does not have a cancer, but actually they had a cancer. Had that certain disease. Now you may understand what is the disastrous thing in healthcare, right? So what we have to, that will lead to a very nice conclusion by the end. Okay, cool. So there's a trick for you to remember. First, how you can remember true positive. True positive means true. You can understand true positives means your whatever positive in that particular sample is. First of all, identify in that problem what is positive and what is negative. Okay, if that problem is a spam or ham, spam means positive. That email is a spam, and ham means the which is negative. The person that email is not a spam. Right? Identify that, and then true positive. What is true positive? The true positive means the examples which your model has classified correctly in positive cases. True negative, the examples which your model classified correctly in negative. True means correct, everything correct. False in false, where your model has predicted false positives, which means that your model has predicted certain things as a positive, but that should be negative. That's why it's false positive, and same goes with false negative. You have to understand logically. Okay. You cannot understand it by ratification. Let's go on another example. Say you have a spam filter that is trained to detect. We have a model, a spam classifier that is trained to detect whether that person has whether the email is a spam or not. Right? The filter is trained on a data set of labeled emails, where some emails were spam and some emails were non-spam. So we have a trained model which is able to classify whether an email comes as spam or non-spam. When that trained model is applied to new and unseen emails, it will make predictions about whether or not an email is spam or not. So how we can infer our model? How we can take inference, or what is the possible scenario when we actually make predictions? Okay, What are the 4 possible scenarios in which after we make the predictions? Assuming that we don't have got any errors in our model. So basically, the first scenario would be the filter which you built. I'm going to take a filter instead of model. The filter which you built, which is able to classify spam and ham, identifies a spam email as a spam. So actually, that identifies the spam email, which means there was a spam email, and your model says that is a spam email. So your model prediction is equals to the actual values. That was an actual email which is classified as an actual spam email that was correctly classified as a spam. That is true positives, right? True negatives is as your model identifies a non-spam email, which is we know that is a non-spam as a non-spam, which we say that is true negatives. And then we have the filter incorrectly identifies a non-spam email. There was a non-spam email, but that model says, that filter says that that non-spam email is a spam. So model says that email is a spam, but actually it was non-spam. That is false positive. And then identifies there was a spam email, but that says as a non-spam, then that is false negative. That was another example. And now we can take this and add it in terms of a table. Add it in terms of a table so that it will make more sense. So if you're seeing in front of me, I have a 2 by 2 matrix sort of thing, right? Over here we have positive, negative, negative, positive. Over here we have the I'd say on x-axis. On x-axis we have actual values. On y-axis we have predicted values. Okay. So first is negative positive, right? Negative positive. So that is that is true positives. Okay, that is true positives. And then we have negative negative, which is false positives. So I think that is bit have to be bit concerned about. And this is called nothing but confusion matrix. So let me just go through you. Yeah, so I think that our writer did a bit of wrong over here as well. I'm so sorry that made me confused. This should be it should be positive. It should be positive instead of negative. It should positive, and it should be negative, right? Now, if that model over here, if the predicted values, it is a predicted value. So if the model says if the model predicts the value is a positive and actually the value was positive, then that's true positive. If the model predicts positive but actually the values were negative, that is false positive, right? If a model predicts that the person what do you say that the particular example is negative, but actually it was positive, then that's false negative. And if the model says that the particular example is negative and actually it was negative, then that's true negative. So diagonal on which you can see, the diagonals were where your model correct classifies the positive samples to positive samples and negative samples to negative samples, and diagonal on this side says the incorrectly classified samples. So this, we have given another name to it, right? Type 1 error and type 2 error. Type 1 error, in the type 1 error, the predicted value is positive, but it is false. Okay, where your model says in type 1 error that your model predicts that the particular example is positive, but actually the actual value was negative. So your model says the person has a cancer, but actually they didn't have. So that is false, right? So model predicts for type that is called the type 1 error. So if anyone asks what is type 1 error, that is false positives. What is false positives? Where your model predicts a negative class as a positive class. Okay, and this is called the type 2 error, which is false negative, where your model says that the predicted value is negative but it's positive. Okay, I hope that it makes sense, and you can and we have already seen T and TP. So basically we have true positives, false negative, true negative, and false positives. And this is called confusion matrix. This is called confusion matrix. This is called nothing but confusion matrix. So let's see a very good example. But before that, we have a very nice conclusion listed out here, which is one of the conclusion which we might not have to miss, right? So let's go and talk about that conclusion. In this scenario, it is important to have a low number of a false positive. Why it is important to have a low number of a false positive? Because it means that user don't want to miss any important emails. Don't want to miss any important emails. Don't want to miss an important email. So for example, if there is an important email and that goes in a spam folder, and but that email is a non-spam, so we are okay if that email is even that we can have a low number of false positives. We should have a low number of false positives. You'll have to apply or logically think in this. This is so logical thing right now. What exactly we are saying, that it is good or it is important to have a low number, because if we have high number of a false positive, which means that all your non-spam emails are going in a spam folder, and most people don't even check that spam folder. So it means that the user will not miss any important emails, while false negatives who might not be as important. False negatives, it's okay, like even spam things comes in a non-spam folder, that's all right for me, right? Because several spam email comes, right? So if you go and check your spam folder, that is, you have a very less spam folder, it's spam emails. But if you go and check your primary, there are a lot of emails which you might even consider as a spam. So basically, even there's a even the false negative increases, which is that the spam email was classified as a non-spam. So that's okay. At least we are not missing any sort of important emails. And on the other hand, we are intellect enough to be careful. So, however, it is still important to minimize the false negative, which means that so that we can refrain from making that spam email to a non-spam. And that's how users have to think from a product perspective. What is more important to me, right? What is more important to me? In this case, false positive is important to me because I don't want to miss any important emails. But we should have a low number of false positives, but false negatives should be also low number, but is not as important as a false positive. So in this case, we tend to have a particular conclusion. So you have to make your model so that it is robust to the false positives, so that it is lowering up the false positives as well as, but not as important, but not giving as much, but giving priority to this false positive, not to false negatives. Understood? Cool. So let's go on the next, which is a numerical example, a very good numerical example of that, so that we could actually talk about things. So basically, what you're seeing in front of me is again this classification, confusion matrix. Why I'm saying classification? It's a confusion matrix. It's a confusion matrix, and in this case, you have. Over here, you have spam and then spam. So basically, on y-axis you have predicted, and on x-axis you have actual values. So your models has predicted 100 samples. Your model has predicted 100 samples which is the true positives. And in this case, your model predicted spam, and that actually was a spam, right? And this is true positives. This is true positives. False positives. That is false positives. That is false positives, where your model says that the particular model had predicted spam, but actually it was not a spam. So that is false positives. There's only 20 examples, which is false positives. And then your model says that the email is not spam, but actually it was a spam. Okay, the predicted was not spam, but actually it was a spam. Okay, where your model says that email is not spam, but actually there is a 5, which is, what do you say, true negatives, where model predicted false negatives, where your model says that the person the email is a non-spam, but actually it was a spam. And there's 175 examples where the models explains that the particular email is non-spam, and your actually was non-spam, so that this is nothing but true negatives. Okay, so you can see over here there's 300 samples, and out of which this was the inferences. So here's how: the number of spam emails, 100 were the number of spam emails that were correctly classified as spam, 175 where the correctly classified as a non-spam, and then false positive where your false positives were this one, false positives, in which case the model predicted spam, but actually that was not a spam. Number of non-spam emails, which was classified, the non-spam emails, the non-spam emails was classified as a spam. And then you have false negative, the number of spam emails that were incorrect classified as a non-spam. So now you see over here that that false positive, which means that the non-spam emails, the false positives out here, where you're actually that was spam, and the model predicted spam, but your actually was not spam, is 20, and we have false negative, which is lower, which is according to what we wanted, right? So we say that we have to minimize this false negative as well as minimize this, but this is more important as compared to this. That's what it's trying to tell in that above statement. You can also take out the accuracy by doing this. Here, what you can do, you can take out the correct for you. What is accuracy? Accuracy means the proportion of a correctly classified, whether it be in a positive or negative class. So correctly means which is true positives. We can add the true positives, the diagonals, and then we can have the by 300, or plus, if you plus all of them, you'll get a 300, which is 0.87, which is 87% of your proportion were correct. But again, you have to be careful. You have to be a bit careful in terms of balancing balanced data and imbalanced data. So I hope that gives you a very good introduction to true positives and true negatives. That is literally very confusing to be honest initially, but as you go in a long run, and as you understand as you understand in terms of what do you say in terms of practicals, and also do work on real world case studies, you will start understanding this true positives and true negatives and all. We also did a numerical example. Now in the next set of lectures, what I'm going to do is talk about precision, talk about recall, talk about F1 score. So precision, how we can utilize this TPFP whatever to take out another useful statistic, measures, and how we can use TPFP and all to take out another useful statistic. And then we have F1 score in which how we can combine both of these two into a single number. And then we have last we have thresholds, which is good for you to understand. Cool. So now let's go and talk about how we can utilize those terms which we have learned about into precision and recall. So precision is a measure of how many of the positive predictions made by the model are actually correct. It is a metric, how many positive predictions, how many positive proportion of your positive predictions in the proportion. Okay, how many in that proportion, how many were correct. That's what precision is. We'll take a look at example. I think it is very tricky if you don't understand. It's very one word kind of thing which you have to understand. Most instructors don't even pay attention to this. It is a metric that can be used to evaluate the performance of a classification model, probably in scenarios where the class distribution is imbalanced. Okay, now we are taking out going to the measures where we are actually dealing like how to evaluate your class distribution is imbalanced, or when false positives are particularly costly. You may not understand even a bit of this. No problem. Let's directly go to an example. So basically, while going to example, which you can see that in a binary classification problem, say for example, the model output is a predicted class for a given instance. They have predicted class label, some class label. So precision is the ratio of the true positive predictions. True positive means your model predicted something positive and actually that was also positive. So we want to take out what number of samples were correctly classified in the positive to the total number of positive predictions. Okay, so assume that a model makes 100 positive predictions and 80 of them were actually true positive. True positive was 80 of them, and 20 were maybe different, where a model has predicted the positive but actually was negative. Okay, so there's only 80 out of 100 positives. I'm talking about, say to this only we are not including negatives. For example, if you have total of 200 data points in your data set, 200 data points in your data set, right, and in that 200 data points only 100 might be for positive samples, and out of 100 only 80 of them were positive. So only 80 of them were positive, which means that the precision would be 80 by 100, which is the proportion, of course, which is 0.8, which means that the 80% of the positive predictions made by the model are correct. So it is not even taking a look at a negative samples. Negative samples means where a model has a predicted different class. It is only focusing on the positive samples out here. Again, I'll repeat the same statement. You have to be a bit careful while learning these. That the precision is the ratio of the true positive predictions, which means that what it is trying to tell, that assume that you have a 200 samples to classify, and out of that, let's go to example. You have a spam and ham. Okay, so you have total spam is a positive and ham is a non-negative. Negative. So you have 200 as a data point, which have the both data points out there, which is spams and hams. We have a 200 data points which include these both categories out here. And now we are interested only in the positives, in the positive samples. So assume that there might be 100 positive samples which has a label as a spam, right? Which has a label as spam, which is the positive samples. Now when you see that, what are the positive predictions which the model made? What are the positive predictions model made out of this 100? Assume that 80 examples where model has predicted as a 80 were true positives, where a model says that is a spam and that actually is a spam, right? But 20 is classified as a where a model says that has a spam, but actually that was negative. So that might be, or other cases. So now 80. So precision. So now what it is telling, precision, what it does is the ratio of the true positive prediction. True positive means the thing which is predicted correctly as well as the actual was also positive, right? To the total number of positive predictions in a model. To the total number of positive predictions. Total number of positive predictions means in this case it will be 100, not 200, because positive predictions was only 100. However, whatever happens, that will actual positive predictions. So that is precision. For example, if you have 100 positive predictions, not including negatives, 100 positive predictions, and 80 of them were actually your model predicted correctly, are actually positive. 100 positive predictions and 80 of them were true positives. Then we say that 80% of the predictions were that precision is 80%. So in simple terms, precision is a measure of how many of the positive predictions made by a model are actually true positive predictions. A higher precision means a lower number of a false positive. So what does it tell? I know that might be confusing, but it is not. It is the easiest thing which you'll ever understand if you want to understand it logically. It is telling how many what is the proportion that your model has predicted What is the proportion? What is the proportion made by the model? What is the proportion of the person having a cancer made by a model is actually the person has a cancer? What is the proportion of a predicted positive values to the actually positive samples? To the actually positive samples. So if your model says that 100, if your model predicts 100 as the person has 100 samples of cancer, but actually 80 have a cancer, right? So 80 by 100, which means that, which 0.8, which is the precision, which means that your model has 80% precision, which means that the 80% of the positive predictions were made by the model are correct. Positive predictions, okay? A higher precision means lower number of false positives. The higher precision means the lower number of false positives. So what does it mean? False positive means, so if assume that out of 100 positive samples, out of 100 positive predicted samples, your model predicted 95 as the samples which are actually also positive. So 95 by 100, which is of course very high. So which is of course 95%, right? So here you are saying what is false positives, where a model predicts positive, but actually it is not positive. That's an error. That's incorrectly classified. So that says that your positive samples is way less. Sorry, the false positive is lower number. So if you have a higher precision, which directly indicates that your false positive, which means that your incorrect predictions in terms of positive samples is less. You have to take a time to understand it. So basically, precision. How do we calculate precision? We simply calculate precision by what are the number of actually positive. The model has predicted the actually correct examples, which are 100, by the 100 plus, which is the true positives, plus false positives, where your model has predicted spam, but actually it was non-spam, but actually it was spam, which is 20 in this case, false positives, right? So 100 by 120, you'll get your precision. Okay. So why do we now? If you have any questions, please ask in a server, because I think this is what you have to apply logical mindset as well over here to understand it. But my point was that false positives. Why are we adding false positives over there? False positive says that the model where actually the prediction was positive. The prediction was negative, but actually it was positive. So we are talking about the total number of positive samples, right? The proportion of the model predicted positive samples by the total number of positive samples. So higher precision means lower number of false positives, which means that lower number of incorrectly classified members. So we use this when your false positives are particularly costly, so that we can worry about if your higher precision. So we are fixing this. So our aim is to, if we have the false positives, if you want to reduce false positives, so you increase the precision. Or if your class data is imbalanced, then we use this precision. Now you may ask, how we use precision when you're actually class distribution is imbalanced? You may ask me about that. Totally all right. Let me make you understand. So let us assume that let's go back to this example so that it makes sense. Assume that normal gene is negative class n, and oncogene is positive class. So in precision will completely ignore this. So basically precision will, out of this 10%, now precision will say, for example, that you have 10 samples which are of on 10 training examples, 10 examples which are on onca-gain, and out of this the true positives were maybe 3 only, where only 3 were predicted nicely. When you 3 were predicted, that out of the 3 samples where that is oncogene, and 7 were the false positives. 7 were false positives, where your model says that, the particular gene is normal gene, but actually it is oncogene, which is positive. So which is nothing but 3 over 10. 3 over 10. 3 over 3 plus 7. Over here it's false positive. False positive, where 7 is the total number of predictions where a model has predicted incorrectly, where it said the positive samples as the negative samples, false positives, plus the true positives, where a model says that the person has an oncogene, as well as actually it was the oncogene, which is 3 by 10. Now it gives you the correct precision. It gives you it gives the correct, it doesn't give the misleading. So now you're able to, so if the precision is higher, which means we can say that your model is robust to this oncogene as well. Okay, I hope that makes sense. That helps in imbalanced data set as well. You can actually go and talk about things if you want. You can also take a look at examples, and also we'll be doing a lot of practicals as well. And this is how we utilize precision to do things for us. In the next set of lectures, we'll talk about recall, F1 score, we'll talk about threshold, and then we are done with this section. So, hey everyone, now we come to our final probably module, is assumptions in logistic regression. So before we talk about assumptions, I want you to really feel why there was a need of assumptions which comes across. So let's imagine a doctor. So there's one doctor, and of course you can say the doctor is any guy. So probably there was a doctor, and then he said that you have a 90% chance of recovery. So this guy said that you have 90% chance of recovery. Usually, okay, fair enough. But the question is, would you trust its statements? Now, would you trust his statements? And then say, okay, fair enough. What do you do? Okay, fair enough. You tell me. But you can only trust if he ran your detailed tests, checked all the matrix, and consulted history to tell you something that it has a 90% chance of recovery, not just from their experience, because we have seen doctor fails. Or probably he has just glanced at your face and just said it, which is a big sign. Or what he did, he based on it on data from 1970. So probably he looked at a lot of and consulted history, or he probably just told based on experience, and probably he just looked at one of the data point in past and then told it's about, okay, fair enough, you might have 90% recovery because there was one patient in 1970 which has similar stuff with you, like you. So now think about your model. How do you know it's making predictions the right way? That's the key question. If it told that the person has a cancer, how would you verify the person has a cancer? Now, when I say when the person has a cancer, is the inner philosophy of logistic regression, that logistic regression assumes that if I take your features, which is like if I take your important features, multiply them with the right weights, which of course we learned by optimization and all, and then apply a sigmoid, I'll get your true probability. But only if this makes sense, this framework of logistic will make sense if the belief and if certain conditions are true, if certain assumptions are true. So these are not these are like assumptions which you test, because then only logistic regression will work like a charm. The first one is the linearity of log odds, which is our first assumption. Now what does this say? This say that the output probability, the output which is coming up, because what we are technically doing, we are taking the linear combination of weights w1 multiplied by x1 plus w2 multiplied by x2 plus w3 multiplied by x3 and all the way around to the wz multiplied by xz. This gives you some sort of z-score. So this, the linear combination, is the input which is going to the sigmoid, then this goes to the sigmoid, should be the linear combination of features. So what does this linear combination means? Linear combination is nothing but, let's imagine something like that. The company wants to decide if a candidate will drop off or not. That's our capstone project. So the judge who is there has few scores, like years of experience of a particular candidate or test score, and whether they were referred or not. So basically what we are doing, we are assigning every feature a weight and then multiplying it, and then we are getting some raw confidence. So basically linear combination is nothing but multiplying each features by its importance, which is the weight in this case, and then adding it all up, and this gives you the linear combination. Now when I say it should be assumed that this follows the linear combinations, that they are linearly separable, something like that, which can be put it out into the sigmoid function. So what does this mean? That the logistic regression says, for me to work properly, I should get a proper z, and z should be the linear combination of weights multiplied by the features, and this is technically a straight line recipe which separates the one classification with another one. That's what it tends to do. So basically it assumes that you have a right way to separate it out, and then I'll take this particular straight line recipe and convert this in S-shaped curve. So to do for this to work properly, this assumes that it is operating on a straight line recipe, and that's why it should be linearly separable. Right? Now that's the first assumption. Another assumption says, sorry, I think I just messed it up. Now another assumption states that there should be no high multicollinearity. So there should be no high multicollinearity. So what does this mean, no high multicollinearity? So let's say that you're building a capstone project which tells whether this person will come into the interview or not, given its experience, total working days and all. So it's very simple. If you have two features, x1 and x2, if they are probably similar, I mean they are probably somewhere similar, then it's like okay, they relate a lot. Like, I mean, they provide the same information, and that's what the multicollinearity means. Multicollinearity is that both features are somewhat similar, but in a different way. So that's why the model sees duplicated or overlapping signals. It does not know whom to believe in. Then the math breaks, and it has huge ways to cancel out the overlap, and the interpretation becomes unstable. So there should be no high multicollinearity. Of course, we have taught about multicollinearity and all those things in our probability lecture, so I would not like to go back. But what it eventually does, both features should not be the same. Another one is, of course, another assumption is no complete separation. So what does it mean, no complete separation? So no complete separation means so the model assumes that given the one feature, I cannot perfectly separate the classes using just one feature. So for example, if a single feature can predict perfectly, which is x1 equals to 1, so you have one feature is always some, and then you have some target variable 1 1 1 and then all 1, x1 equals to 1. So of course this will the logistic regression will always tell, okay, this prediction is going to be 1. So there should be more than one feature to be able to perform it well. So it cannot perfectly separate the classes using just one feature. It needs a multiple input variables to be able to make some patterns out of it, and then make some coefficient to be able to derive to these answers. Now, another one, the fourth assumption is, which is large enough sample size. So it means I've seen enough data to learn stable weights. So you have seen enough observation so that I'm able to predict it nicely, so that I'm able to tweak and get my loss to the down so that my weights are good, and if the weights are good, my predictions probability will be also good. So these are 4 assumptions of logistic regression, which is super important. There are some other assumptions as well, but what it says that the assumption number 1, that linearity, it should be linearly separable. Multicollinearity, not all the features should be same. Complete separation, it should have lot of features to be able to perform perfectly, and it should be having enough sample size to be able to perform nice. So why we learn about assumptions? Assumptions can be super valuable if you do something. So let's say that you have high multicollinearity in your data set. So you have a data set which looks something like this: x1, x2, x3, x4, x5, x6, x7, and all the way down to y1. this is the plan, right? This is the particular plan. And then you have some data in here, then you have some data in here, all the way down. Now say that x1 and x2 are somewhat similar but amplified. So because you know that assumptions are being violated, what do? You drop any one of them feature, any one of the column, based on of course your understanding of business problem. And then you just are left with one of them, so that model will not just will not look at both of the ones. So this is how assumptions helps to tweak something in data for your algorithm to perform better. And that's what people miss nowadays, that people do not know, okay, I need to fix some stuff in my data which assumes something, every algorithm which assumes something to be able to perform something better. So yeah, this is the point which I'm trying to make. So this is it about assumptions. Now, what your task is, that you'll be getting enough number of tasks. We have taught you the fundamentals and the core thinking principles now. Now your task is that you'll go on DataWars. DataWars is a data science practicing platform. You can also purchase like $30 for 6 months, which is crazy because they have around $249 per year. So I just talked with them. There are partner companies to be able to get you in $30, or you can just continue for free as well if you'd like, because they have several projects. So we're going ahead doing practice. You'll be doing practice in DataWars itself. It's a very guided project for you to be able to do it. And then you have a capstone project to develop on your own by asking our TAs and stuff to be able to build a good project. So the capstone project and all that thing is in the next set of videos where you see how to talk, you see how the things should be there, and how to write a project and how to do it like a thinking mindset. We have published several project materials in past. You can just look at it on the thinking process to be able to develop it. But you can apply the same thing in this capstone project, or follow the guidance which is given out there in the capstone project to develop something nice. So I hope it makes sense. Let's catch up in the next one. Tab tak ke liye, bye bye, see you.